Hello friends, IBM is here with another episode of Learning Physics, and I hope this is going to be, if not the last, is the second last episode of electricity. Remember, we are dealing with the solved past paper questions in AS Physics. This is Physics 9702. That is paper 2. We are solving past paper questions. This time we are dealing with electricity and DC circuits, and this is going to be part 4 of these episodes. This is actually part 4. Do not forget, within this unit we have been discussing questions about current, potential difference, EMF, resistance. We have been dealing with Ohm's law many times. We have been seeing electric power and efficiency, the IV characteristic graphs, Kirchhoff's laws, potential dividers, and we expect a lot more from this unit. So without wasting time, I would like to take you to where we stopped in part 3 so that we continue solving these questions that we have. Don't forget, download the document. You can print the document per topic so that you work out in a hard copy. You follow through a hard copy. You cannot just follow these videos by just watching on YouTube and that's all. It's better you try to practice on hard copies so that following becomes a little bit easier. So I think in part 3 we must have stopped on page 416, and I want us to start from the same page, 416. So what is wrong with this page? So I think in part 3 we stopped on page 416, and I want us to begin from page 417. So this is the first question. A battery connected in series with a resistor R of resistance 5 ohms is shown in the figure. The EMF of the battery is 9 volts and the internal resistance is R. The PD across the battery is 6.9 volts. That is going to be the terminal PD. Because the EMF is 9 volts, so the terminal PD between the terminals is 6.9 volts. That is across the battery terminals. Use energy consideration to explain why the potential difference across the battery is not equal to the EMF of the battery. So we see that there is an internal resistance somewhere there, and it is the only way we can explain why the EMF is not equal to the terminal PD. So EMF is actually total energy available per unit charge, and some of the available energy is used or it is dissipated in the internal resistance of the battery. That's why the EMF is not equal to the terminal PD. So we can simply say that EMF is equal to the total energy available. Total energy available per unit charge. Total energy available per unit charge, that is the EMF. However, some energy or some of the available energy is used in the internal resistance. I want to use the most appropriate term, which is dissipated or is lost. Some of the available energy is lost, is wasted, is dissipated. Is dissipated in the internal energy. I mean in the internal resistance. In the internal resistance of the battery. So not all the 9 volts goes outside, some of it is wasted within the battery, warming up the battery. Calculate the current in the circuit. Okay. To find the current in the circuit, since we have the terminal PD, we can easily find the current. So the current is going to be V over R. The terminal PD is 6.9 and the resistance outside is 5.0. So this gives us 1.38, I guess. 6.9 divided by 5. I think that's 1.38. So the current is 1.38 amperes. Then calculate the internal resistance R. Internal resistance R, remember we have said the EMF is equal to the terminal PD plus the lost volts. The EMF is 9, the terminal PD is 6.9 plus the lost volts. Lost volts will be current times the internal resistance R. So since we have I there, it means 9 minus 6.9 should be equal to the current, which is 1.38 times the internal resistance R. So I'll just say 9 minus 6.9 divided by 1.38, which gives us 1.52. So the internal resistance is 1.52. Then calculate for the battery in the circuit the total power produced. Of course, total power produced is equal to EMF times the current through the battery. So the EMF is 9, the current through the battery is 1.38. So total power is going to be 9 times 1.38, which is 12.42, 12.4 watts. Then the efficiency, of course, we know that efficiency is power output over total power input. Efficiency is equal to power output over total power input, or over total power input. If you want, you can change it as a percent, express it as a percentage, but there is no need for that. So the output is equal to I times the terminal PD, and the input is equal to I times the EMF. So I cancels because they're in series, the current is the same. So this is going to be 6.9, that is the terminal PD over the EMF, which is 12.4. I mean over, that is not 12.4, it is 9. So this is going to be 9. So this is going to be 6.9 divided by 9, which is 0.76 recurring, which is 0.77. So that is 0.77 or 0.767. Yeah, let me write 0.767 because 6 is recurring. Or this can be converted to percentage, so that will be 76.7% if required. Alternatively, you can multiply current times V, you multiply current times E, but that will be repetition, you'll be wasting a lot of time. That still gives you the same efficiency. A power supply of EMF 240 volts and 0 internal resistance is connected to a heater as shown in the figure. The wires used to connect the heater to the power supply each have length 75 meters. The wires have a cross-sectional area of 2.5 millimeters squared and resistivity of 18 nano-ohm meters. Nano-ohm meters, that is the resistivity. The heater has a constant resistance of 38 ohms. Show that the resistance of each wire is 0.54. So they have given us resistivity, we have the cross-sectional area, we have the length. So we simply say resistance is equal to rho L over cross-sectional area. So this is going to be rho is 18, but it is nano, so it is 18 times 10 power negative 9. Then times the length, which is 75, divided by cross-sectional area, which is 2.5, times, we convert from millimeters squared to meters squared, I think that's 10 power negative 6. So this will be times 10 power negative 6. So this will give us 18 exponent -9. Okay, let me close that bracket, times 75 divided by 2.5 exponent -6. So this gives us 0.54. So this is 0.54 exactly. Then calculate the current in the wires. Of course, since we have the resistances, we have the EMF. The heater has a resistance of 38. This is 38 ohms. The wire, the resistance of each wire is 0.54. That means, and there are two wires. There is this one and there is that one. So we are most likely going to multiply this by 2 to get the total resistance. So this wire has a resistance of 0.54. The other one also has a resistance of 0.54, and they're in series. So current is going to be equal to EMF divided by total resistance. The EMF is given as 240, and the total resistance is going to be 38 plus 0.4 plus 54 plus 0.54 plus 0.54. So that is going to be our total resistance. So we just pressed our calculator here. So 240 divided by 38 plus 0.54 plus 0.54. So that gives us our current as 6.1. So this will be 6.1 amperes. Calculate the power loss in the wires. Power loss in the wires. Power is equal to I squared times R. And we want the power loss in the wires. Remember, there are two wires, so total resistance is 0.54. The current is the same, which is 6.1. So the power loss is going to be 6.1, I think it is 6.14 squared times the resistance. Total resistance of the wires is 0.54 plus 0.54 because there are two wires. So that would be 6.14 squared times 0.54 plus 0.54. So we are seeing our answer as 40.7 or 41. So this will be approximately 41 watts. The wires to the heater are replaced by wires of the same length and material, but having a cross-sectional area of 0.50 millimeters squared without further calculations. So the examiner should not see you doing some calculations. State and explain the effect on the power loss in the wires. So we know that resistance is inversely proportional to cross-sectional area. Because the length is the same, resistivity is the same, they are from the same material. But you notice that the cross-sectional area has actually decreased from 2.5 to 0.5. In other words, the cross-sectional area has reduced by a factor of 5. Therefore, if the cross-sectional area reduces, it means the resistance is going to be greater. Therefore, R or resistance is greater. Resistance is inverse. Let's begin by saying resistance is inversely proportional to area. Resistance is inversely proportional to area. Therefore, the resistance is greater. The resistance is greater. By the way, if resistance is greater, the current does not remain constant. If resistance is greater, it means the current reduces, because note that current is inversely proportional to the resistance for the same EMF. So from power equals to V squared over R, if the resistance is greater, it means it means the power loss in the cables is going to actually be okay. The resistance is inversely proportional to area, therefore resistance is greater. What does this imply? It implies that the power loss in the cables, in the wires, is going to be greater, sorry, is going to be smaller, and therefore the power loss in the cables will be, the PD across the wire is going to be greater. If the resistance is greater, the PD across the wire is going to be greater because they told us the wire to the heaters are replaced by wires of the same length and material, but having a smaller cross-sectional area, which means the resistance of these wires is going to be greater. And if the resistance of the wires is greater, for the same current flowing, if the resistance is greater, it means the power loss is going to be greater in the wires. Simply because the PD across the wires is going to be greater. So let's say PD across the wires is greater. And if the PD across the wires is greater, even though the resistance is greater, the resistance becomes greater, the PD is squared. So the PD across the wires is greater, so the power loss in the wires increases. The power loss in the wires increases. You could also look at it in a simpler way, in another way. That is, power is equal to I squared times R. If the resistance increases and the power is not changing, I mean the current is not changing, then it means it is only because the PD across the wires increases. And if the PD across the wires increases, it is as easy as looking at the power being directly proportional to the resistance. Therefore, increase in resistance means more power is going to be lost in the wires. A heater is made from a wire of resistance 18 ohms and is connected to a power supply of 240 volts. The heater is switched on for 2.6 megaseconds. Calculate the power transformed in the heater. So power is equal to V squared over R, and V is 240, which is squared, divided by R, which is 18. So the power is 240 squared divided by 18, which is 3,200. Then the current in the heater. Determine or calculate the current in the heater. So current is equal to V over R. V has been given as 240 and R is 18. That is very easy. So 240 divided by 18, which is 13.3. Then the charge passing through the heater, charge is equal to I times T, where I is 240 divided by 18, and then times T, they gave us T as 2.6 megaseconds, so that is 2.6 times 10 power 6. So I will just multiply that answer by 2.6 exponent 6, which is 3.47 times 10 power 1, 2, 3, 4, 5, 6, 7 times 10 power 7. So that is 3.47 times 10 power 7. Then the number of electrons per second passing a given point in the heater. Remember, charge is equal to the number of electrons times the charge of each electron. So number of electrons is going to be the total charge, which is 3.47 times 10 power 7 divided by the charge of each electron, which is 1.6 times 10 power negative 19. So I'll just divide this by 1.6 exponent negative 19, which is 2.17 times 10 power 26. So that's the number of electrons per second. two resistors A and B having resistances R1 and R2 respectively. The resistors are connected in a series with the battery as shown here. The battery has EMF E and zero internal resistance. State the energy transformations that occur in the battery. Of course, in the battery we have chemicals, so it is chemical energy to electrical. So in the battery we have chemical energy to electrical. Then of course in the resistors now it is already electrical, so it must be converted to thermal energy. So it is electrical energy to thermal energy. That is electrical energy to thermal energy in the resistors. Okay. The current in the circuit is I. State the relation, the rate of energy transformations in the battery. In the battery, the EMF is E and the current through it is I. We want the rate of energy transformation, that is power. So power is going to be E times I. So power, the rate of energy transformation, that is power. So the power is going to be E times I. Or uh, because E is going to be equal to the current I times total resistance, which is R1 plus R2, we can also say power is equal to I squared into R1 plus R2. That is I times total resistance. Then the resistor A. The current in the circuit is I. State the rate of energy transformation in resistor A. So for resistor A, power in resistor A is going to be equal to the current through resistor A, which is going to be I squared, times resistor A, which is going to be R1. Is it R1? Yes. So that is R1. So the answer here is going to be I squared R1. Okay. The resistors are made from metal wires. Data for the resistors are given in the figure. So they have given us resistor A, B, resistivity, length of the wire, and the diameter. Use information to determine the ratio power dissipated in A over power dissipated in B. So because we want power, and power is I squared R, by all means, although the current is the same, we need to find the resistance. So resistance is equal to rho L over cross-sectional area. And they have given us diameters, so we shall remove area. We know that area is equal to pi d squared over 4. So the resistance, the ratio that we are looking for is going to be equal to I squared. Of course, the current is the same, resistance of A divided by I squared, resistance of B. So then we substitute. I'm just going to combine pi d squared over 4 with the area so that I come up with expressions. So I will start with A. I has cancelled out. So for A, Ra is going to be rho times the length divided by the cross-sectional area, which is going to be pi, because for A diameter is d, so the cross-sectional area is going to be pi d squared. The 4 goes up. Then I divide this by, for B, it will also be 4. Resistivity is rho over 2. The length is L, divided by the diameter. So this is pi, diameter is twice d. So some quantities here have cancelled out. I'll cancel them out. 4 pi has cancelled out. L has cancelled out. Then 4 has cancelled out. So this will simplify to, okay, maybe people cannot see that L has cancelled out. So this simplifies. Maybe let me show this 4 rho L over pi d squared times, we get the reciprocal. In the numerator, I will have 2 pi d divided by this is squared. So it becomes 4 pi d squared because it is squared. Divided by, this is going to be 4L times rho over 2. So that's why I've been saying 4L has cancelled. And by the way, pi d squared cancels, rho cancels. So you remain with the numerator has 2 divided by 1 over 2. So that is 4 divided by 1 over 2, which becomes 4 times 2, which becomes 8. So the ratio there is 8. The resistors A and B are connected in parallel across the same battery of EMF E. Determine the ratio power dissipated in A over power dissipated in B. The resistors are connected in parallel. Now that they are connected in parallel, the PD across them is the same. So here power is going to be V squared over R, or this would be the same as the EMF squared over R because it is the battery EMF which will be the PD across each. So we can now look at the ratio of power of A, which will be V squared over RA, divided by the power of B, which will be V squared divided by R of B. When you simplify this further, we get the reciprocal, so it will be R of B over R of A because V squared cancels out. And we have seen that R of A over R of B is 8. That means R of B over R of A is going to be the reciprocal. So this is going to be 1 over 8. And this is going to be, I think that is 0.125. 1 divided by 8, that is 0.125. 0.125. The battery of EMF 20 volts and 0 internal resistance is connected in series with the two resistors R1 and R2 as shown. The resistance of R2 is 600 and that of R1 is 400. Varies from 0 to 400. Calculate the maximum PD across R2. Maximum PD across R2, we are using potential dividers, so V out is going to be equal to R2 over total resistance R1 plus R2 times the voltage supply Vs. So I'm going to say V across R2 is going to be R2 over R1 plus R2 times the voltage supply, which is going to be R2 is 600. Total resistance, they have said we want maximum. So PD across R2 is maximum when the resistance R1 is 0. So this is going to be 600 over 0 plus 600. Then times voltage supply, which is 20. So the answer here is going to be 20 volts. Then the minimum PD across R2. PD across R2 is going to be minimum when the resistance R1 is maximum. So V here is going to be equal to 600 divided by the other one is 400 plus 600 times the voltage supply, which is 20. And this is going to be 600 divided by 1000 times 20, which is 12. So minimum is 12. A light-dependent resistor is connected in parallel with R2, as shown in the figure. With the light intensity, when the light intensity is varied, the resistance of the LDR changes from 5 to 1.2. That means the light intensity is increasing because light intensity is resistance of the LDR is inversely proportional to the light intensity. For the maximum light intensity, that means the resistance is minimum. they made maximum bold. The resistance must be minimum, which is 1.2 kilo ohms. Calculate the total resistance of R2, and the LDR. So they are in parallel. So resistance in parallel is going to simply be the product over the sum. Or you can use 1 over R parallel is equal to 1 over 600 plus 1 over 1200. But this is the same as getting the product 600 times 1200 divided by the sum, which is 600 plus 1200 for resistors in parallel. I think this is 4000. 600 times 1200 divided by 600 plus 1200. Is it? Let me check it again. 600 times 1200 divided by 600 plus 1200. It is 400. The resistance of R1 is varied from 0 to 400 in the circuit of the figure and 6.1 and 6.2. State and explain the difference, if any, between the minimum PD across R2 in each circuit. Numerical values are not required. Although numerical values are not required, you can check numerically and before you come up with your answer. However, I want you to note that the total resistance in parallel for the R2 and LDR is smaller. Total resistance is smaller because the resistance of R2 and LDR has reduced. That means if I was finding the PD across R2 in the second case, it is going to be the resistance of R2, which is 600, over total resistance, which will be 400, because we are looking for minimum PD. So it will be 400 plus 400. 400 for parallel combination plus 400 for the other variable resistor, which has a maximum of 400. When you multiply this by the voltage supply, which is 20, the value obtained is actually going to be less. We can verify 600 divided by now 800 times 20. Actually, the value is going to become bigger. No, that is not the PD across. That is wrong. This is going to be 400 because the PD across 600 is the same as the PD across the LDR. So that will be 400 over 800, which is a half. 400 over 800 times 20, which is 10. Okay. So the PD is going to be smaller because the PD across 600 ohms is the same as the PD across that, which is the PD across the total parallel combination, which is 400. So we are saying the total parallel resistance of R2 and LDR becomes less. Remember, the PD depends on this resistance. Becomes less than R2 alone. So the minimum PD is reduced. So the minimum is reduced. So when we put the LDR in parallel to R2, in parallel with R2, it means total resistance becomes smaller, so the minimum PD across R2 becomes less, because the PD across R2 is the same as the PD across the LDR, which will be the PD across the total resistance in parallel. A battery of EMF 12 volts, internal resistance R, is connected in series to two resistors, each of constant resistance X. The current I1 is 1.2, so this is 1.2 amperes. The same battery is now connected to the same two resistors in parallel. then I2 is 3.0 amperes. Show that the combined resistance of the two resistors, each of resistance X, is 4 times greater in figure 5.1 than in figure 5.2. So let us start with the figure 5.1. Figure 5.1. Figure 5.1, total resistance is equal to twice X because they're in series. Total resistance is twice X. We want to show that the combined resistance of the two resistors in each of resistance X is 4 times greater in figure 5.1 than in figure 5.2. In figure 5.2, they are in parallel. In figure 5.2, resistance in parallel, this was resistance in series. Resistance in parallel is going to be x times x over x plus x, which is x squared over 2x, which is the same as x over 2. Then we can now divide and see. So resistance in series divided by resistance in parallel. This is going to be 2x divided by x over 2, which becomes 2x over 1 times we get the reciprocal 2 over x. And you and me will see that x cancels out. So x cancels out. So this is equal to 4. That means resistance in series is equal to 4 times resistance in parallel. So it means the combined resistance of the two resistors, each of resistance X, is 4 times greater in figure 5.1, that is in series, than in figure 5.2, which is in parallel. Okay. Explain why I2 is not 4 times greater than I1. Why isn't, we have seen that I2 is 3.0, but I1 was 1.2. The question is explain why I2 is not 4 times greater than I1. Why hasn't I2 increased 4 times greater than I1? Note that there is an internal resistance in the battery. If there was no internal resistance in the battery, then automatically I2 would be 4 times I1. But since the total resistance, although resistance in series is 4 times resistance in parallel, total resistance is not actually 4 times. It is not actually 4 times the other one because we add this small r here. So we can simply say that since there is internal resistance, total resistance for series, circuit is not 4 times. Is not 4 times greater than resistance in parallel. It is only for the two resistors which is 4 times, but the total resistance including the internal resistance, it is not 4 times greater than the resistance is not 4 times greater than the resistance for the parallel circuit. Hence, also, I2 cannot be 4 times greater than I1. So I2 cannot be 4 times greater than I1. But if there was to be no internal resistance, it would automatically be 4 times greater. Use Kirchhoff's second law. Using Kirchhoff's second law, state equations in terms of EMF, current X and R for the circuit of figure 5.1 and figure 5.2. So here I will choose a loop in that direction, which is clockwise. Sum of EMFs is 12. Sum of PDs, we have X and X, that is 2X. So we have I1 times 2X. Then plus, we have I1 times small r. Or we can say 12 equals to I1, which I1 is 1.2, into brackets, we have 2X plus small r. So this can be our equation. So we shall simply say the sum of EMFs, we have only one, which is 12, equals to the current, which is 1.2 times total resistance, because they're in series. So that is 2X plus R. That is the total sum of the PDs. Then for circuit 2, these two resistors are in parallel, so the total resistance is X over 2. The resultant is in series with R. So sum of EMFs is still 12. If I put in a loop, I put in a loop in the clockwise direction. The sum of the EMFs is 12 equals sum of PDs. We have I2 times small r plus total resistance here in the parallel is X over 2. The current is I2. So that is going to be I2 times X over 2. Because I2 here is 3, I'll simply say that this is 12 equals to 3.0 into brackets R plus X over 2. So that can be our equation. So we have this as 12 equals to 3.0 into R plus X over 2. Use these equations in Roman 3 to calculate the resistance X. So let's try to solve these equations. Let's simply try to solve these equations. So I can solve them, I think I can solve them easily by equating them because they seem to be equal. They seem to be equal. Alternatively, if you don't want to do that, you can just combine them in any way you want. However, I can say for the first equation, can I simply say 1.2 into 2x plus r should be equal to 3.0 into r plus x over 2, because all the two equations are equal to 12. That's why I'm equating them. So I'm going to open brackets and collect like terms. So 1.2 times 2, that is going to be 2.4x plus 1.2r is equal to 3.0r plus 3x over 2. Okay. So when you multiply, let me see, that's 1.5, 2.4. No, I think that will not work for me. I have to use an elimination method. Let me use an elimination method to be able to solve this. I will use an elimination method. This will not work. So we are solving two simultaneous equations. So let me use elimination method, or you could use substitution. So let me first simplify the first equation. The first equation is going to be 12 divided by 1.2. So 12 over 1.2 is equal to 2x plus r. So 12 divided by 1.2 is 10. So we say that 10 is equal to 2x plus r. That's for the first equation. And for the second equation, we have that 12 over 3.0 is equal to r plus x over 2. I think 12 over 3 is 4. 4 is equal to r plus x over 2. So you can maybe subtract the two equations so that R disappears. So I'm going to say 10 minus 4 is equal to 2x minus x over 2. R has disappeared when I subtracted the two equations. So I have that 6 is equal to 2x minus x over 2. All this mathematics is wastage of time. If you can solve this very fast, easily, it is fine. So I'm just cross multiplying everything by 2. So I have that 12 is equal to 12 is going to be, this is 4x minus x. So 12 is equal to 3x, or 3x is equal to 12, which means x is going to be equal to 4.0. So x is 4.0. For any method that you use, you can find x. If they wanted us to find r, we could go back and substitute and find r from in any of the equations. For example, 4 is equal to r plus x over 2, which is 4 over 2. So it means R would be equal to 2 ohms. Because this is 2, take it the other side, R would be 2 ohms. Calculate the ratio power transformed in one resistor of R of X in figure 5.1 to that power transformed in one resistor of resistance X in figure 5.2. Okay, so power is going to be I squared R, or V squared over R of IV. So power is equal to I squared R. Or you could use V squared over R if you have the PD. Or you could use IV. So let's find a ratio. We are looking at one resistor. For a resistor in the figure, I will just use I squared over R. For a resistor in figure 5.1, the current is 1.2, so that's 1.2 squared times the resistance we have seen is 4.0. Divide by, for a resistor in the second figure, because they're in parallel, the current divides. So this is, if this is 3.0, so this should be 1.5, and this is 1.5. Because they are identical, the current divides equally. So for the resistors in parallel, the current is going to be 1.5. So I'll say 1.5 squared times 4.0. So I now press the calculator. 1.52 squared times 4 divide by 1.5 squared times 4. So that is 16 over 25, which is 0.64. The resistors in the figure 5.1 and figure 5.2 are replaced by identical 12-volt filament lamps. Explain why the resistance of each lamp when connected in series is not the same as the resistance of each lamp when connected in parallel. We have seen a similar question. When the lamps are in parallel, the PD across them is higher than when they are in series. In series, the PD divides. So if the PD is higher, it means if the PD is higher when they are connected in parallel, then it means that the resistance of this lamp is actually going to be changed. It is going to change. The PD is greater when they're in parallel, so it means the resistance must change. By the way, the PD is less when they're in series, because if they're in series, the PD from the EMF of the battery is divided equally. But if they're in parallel, the PD if they're in parallel, the PD of the battery is the same as the PD across them. So that means if resistance is equal to V over I, it means that actually the resistance of the lamp is actually going to be greater when they're in parallel. So explain why the resistance of each lamp when connected in series is not the same as the resistance of each lamp when connected in parallel. If you're not very sure, you just simply say that the resistance of a lamp changes with the PD, changes with the potential difference. changes with the PD across it or with the current through it. With the current, it changes with the current through it. The PD across the resistance of the lamp changes with the PD or with the current across it, and we know that the PD or the current is greater in a parallel circuit, and the PD or the current is greater in a parallel circuit. In a parallel circuit, so R changes. So the resistance changes. Or you would talk about the PD or the current is less in a series circuit, so the PD changes. It is greater in a parallel circuit, it is less in a series circuit. So I'm saying, or you would say V or I is less in a series circuit. So the PD changes. So the resistance changes. So R will not be the same. A cell with internal resistance supplies a current. Explain why the terminal potential difference is less than the EMF of the cell. We have said EMF is the total energy available per unit charge. If there is an internal resistance, some energy is dissipated in the internal resistance of the cell as lost volts. So some energy is dissipated in the internal resistance of the cell. In bracket, those are called lost volts. They are responsible for warming up the battery. A battery of EMF 12 volts, internal resistance 0.5 is connected to a variable resistor X and a resistor Y of constant resistance as shown here. The resistance R of X is increased from 2 to 16. So the resistance is increased from 2 to 16. The variation with R of the current I in the circuit is shown there. Calculate for I equals to 1.2, the PD across X. So 1.2, this is 1, 2. 1.2 is here, and the resistance is 6. So PD is equal to I times R. I is 1.2, V is 6, R is 6. And I think that is 7.2. 1.2 times 6. I think that is 7.2. So that is 7.2. Then the resistance of Y. We have seen the resistance of X as 7.2. So this is 7.2. And the current given here is 1.2. So current is 1.2. I is 1.2. So we want to find X. Remember total current I is equal to the EMF over total resistance R total. Where they are in series, we just sum them up. So we shall simply say that total current I is equal to the EMF over total resistance. So total current is 1.2, the EMF is 12 volts, total resistance is going to be the internal resistance, which is 0.5, times resistance of X, plus resistance of X, which is 7.2, plus resistance of Y. So I'm just cross multiplying, so I have 0.2 plus 7.2, that is 7.7, plus resistance of Y is going to be 12 divided by 1.2, which is 10. So it is 10. So it means resistance of Y is going to be 10 minus 7.7, which is 3 point, is it 3? Did I sum up the resistances correctly? Hmm, 7.7, 12 divided by 1.2, that is 10 minus 7.7, that is not true. The PD across, okay, let me use a different approach. Okay, let's just use a simple expression which involves getting the PD across X. So PD across, not PD across, PD across Y is going to be, we have the PD across X as 7.2. So the PD across Y is going to be 12 minus 7.2, which is going to be equal to 12 minus 7.2, which is, I think that is 4.8. That is 4.8. That is the PD across Y. And if Y is in series, with if Y is in series, so the PD across Y is 4.8. But then remember, resistance is equal to that PD divided by resistance is equal to the PD divided by resistance is PD divided by the current. But there is another resistor which is the internal resistance. So this 4.8 is PD across Y and small r, not only the so this is a mistake. The PD is across Y and a small resistor because there are two resistors which are not catered for. The PD across Y and a small internal resistance is that. So the the resistance of Y plus the internal resistance, which is small r. Let me make this small r. Okay, yeah. The resistance of Y plus small r should be equal to the PD across them divided by the current through them, which is going to be the PD across these two is 4 ohms divided by the current. The current through them is going to be 1.2. This is 4.8 divided by 1.2, which is, I think, 4. So R plus small r is equal to 4. That means Ry is going to be equal to 4 minus, it is 4 minus small r, which is 0.5, which I think is going to be 4 minus 0.5, which gives us 3.5. I think that is correct. 3.5 ohms. Okay. Alternatively, I want to use another method. Let me try it here. So total resistance, R total, I'll quote R total, is going to be the EMF, which is 12 over the total current, which is 1.2. And this gives us, I think, 10 ohms. That is 10 ohms. But total resistance is going to be X, resistance of X, plus the internal resistance, small r. This is equal to 10 ohms. So X plus small r should give us X plus small r should give us the resistance of Y. What is the resistance of Y? I mean the resistance of, okay, the resistance of X plus small r plus the resistance of Y should give us total resistance of 10 because they are in series. Then let's check out for resistance of X. X is 6, I guess. X is 6. Internal resistance is 0.5 plus the resistance of Y gives us the total as 10. So that means the resistance of Y is going to be 10 minus 6.5, which is equal to 3.5. Yes. So here, the other method I started with, I was using PD as resistance instead of finding the resistance from the graph for X. Okay, so that is going to give us 3.5 ohms. The power dissipated in the battery. We want power in the battery. Power in the battery. In the battery, we have a resistor which is of resistance R. We're not looking for the power generated by the battery. We want the power dissipated in the battery. So that is power is equal to I squared times the internal resistance, which will be 1.2 times the internal resistance, which is 0.5. And I think this is 0.72 without even calculating. 1.2 times 0.5, that is 0. Sorry, this is squared. 1.2 squared times 0.5. Okay, that is 0.72. Use the figure to explain the variation in the terminal PD of the battery as the resistance R of X is increased. So we are using figure 7.2, which is actually the graph, to explain the variation in the V, terminal PD, V, as the resistance R of X is increased. So we know that EMF is equal to the terminal PD plus V plus the lost volts, that is VR. So we of course terminal PD is equal to I times R. So I make the lost volts the subject, maybe VR lost volts is equal to the EMF minus the terminal PD. But remember the terminal PD is equal to I times R. So the lost volts VR is going to be equal to the EMF minus I times the resistance R. So as R increases, we are seeing that as R increases, the difference between E minus IR becomes smaller, which means the lost volts also becomes smaller. And if the lost volts become smaller, that is enough to imply that the terminal PD increases as R is increased. But of course, the current decreases. So that means there is a smaller loss in PD across the battery. There's a small lost volts in the battery. That's what it means. Therefore, terminal PD increases, terminal PD increases as R increases. Terminal PD increases as R increases, but we are seeing from the graph that the current decreases. The current decreases, so there are less lost volts. The lost volts decreases as the resistance increases, because as resistance increases, the terminal PD increases, but the current is decreasing. So the lost volts is going to be I times small r. So the current becomes smaller, so the product becomes smaller. That means there are less lost volts. A battery of EMF 4.5 internal resistance R is connected in series with a resistor of resistance 6 ohms as shown in the figure here. The current I in the circuit is 0.65 amperes. Determine the internal resistance R of the battery. So I have just mentioned that total current is equal to the EMF divided by total resistance. So the current is 0.6 and we want to find the total resistance. So the current is 0.65 equals to the EMF of 4.5 over 6.0 plus the internal resistance of R. So it means we shall simply say that 6 plus R is equal to 4.5 divided by 0.65. So I'll say 4.5 divided by 0.65, which is that, minus 6, which gives us 0.92. So R is 0.92. So that is 0.92. Then determine the terminal PD of the battery. Determine the terminal PD of the battery. So from V equals to IR, and we have that I is equal to 0.65. We want the terminal PD, so the current is 0.65. So V is going to be 0.65 times 6, which gives us 0.65 times 6, that is 3.9. Then the power dissipated in the resistor, of course, power in the resistor is going to be equal to I squared R, or it can be V squared over R if you know V, or it can be IV. So I'll use one of those. Let me use the one of PD. So power is going to be V squared over R, which is 3.9 squared divided by 6. 3.9 squared divided by 6, that is 2.535. So that is 2.5 watts. Then the efficiency of the battery. So we know that efficiency is equal to power output over power input. If you want it as a percentage, you say times 100. The power output of the battery is got from the power dissipated outside, or is got from the terminal P, the power going to the terminal PD, which is going to be I squared times R outside. The power generated inside the battery is going to be I squared into R plus R. Or it can be I times V over I times E, which is going to be, of course, I cancels. So V is, that is the terminal PD is 6, and then the EMF is 4.5. The EMF is 4.5. So we just get 6 divided by 4.5, and the ratio is it true? Let me check. The efficiency of the battery, what is output is, no, V is not 6. What is V? V is 3.9. PD outside is 3.9. So 3.9 divided by, I think the EMF is 4.5. Yes. So that is 0.866 recurring, 0.867 or 0.867, or you can write 86.7%. A second resistor of resistance 20 ohms is connected in parallel with the 6 ohm resistor in the figure 5.1. Describe and explain qualitatively the change in the heating effect within the battery. So we have a resistor of 20 ohms connected in parallel with this one, which is, so we are putting here another resistor in parallel, which is of 20 ohms. So the effect is that total resistance here reduces because they're in parallel. And the heating effect, if the total resistance here reduces, it means the current which goes through the battery is going to be greater if the total resistance here has decreased. And if the current going through the battery is greater, it means the lost volts, which is current times R, is going to be greater because of a higher current. Therefore, more power is going to be dissipated in the battery. So we are saying that the circuit resistance decreases. So the current increases. So the current through the battery increases. So the current through the battery increases. Remember, power dissipated in the battery is equal to I squared times R. So it means there's going to be more heating effect within the battery because of a higher current. Hence, more heating effect. Hence, more heating effect in the battery. More heating effect in the battery. Okay. Hence, more heating effect in the battery. A battery of EMF volts and internal resistance 0.5 is connected to two identical lamps as shown here. They're in parallel, so the terminal PD is the PD across each of these cells. I mean these lamps. Each lamp has a constant resistance. The power rating of each lamp is 48 watts when connected across 12 volts. Explain why the power dissipated in each lamp is not 48 watts when connected as shown in the figure. So the PD across each lamp is going to be less than 12 because they are rated 48, 12 volts, and yet we see that there's an internal resistance here. So the PD across each lamp is not going to be 12 volts, so the power will not be 48. So the PD across the lamp is not, or is less than, actually it is going to be less than 12 because of the internal resistance is less than 12 volts since there is, or since there are lost volts. Since there are lost volts in the internal resistance. Because there are lost volts in the internal resistance, it means the PD across the lamps is less than 12 volts. That means the power cannot be 48 watts. So, power can't be or cannot be 48 watts. It was only 48 when the PD is 12 volts. Then calculate the resistance of one lamp. So resistance is equal to V squared over P, from P is equal to V squared over R. Or you could use V is equal to IR, but I will use this one directly, where V is going to be 12 squared and the power is 48. So 12 squared divided by 48, that gives us 3. So this is 3.0. Then calculate the current in the battery. Of course, current is equal to the EMF over total resistance, R total, which is going to be R plus the internal resistance. So this is going to be, the EMF is 12 over our total resistance. We have the resistance of each lamp is 3, but they're in parallel. So resistance in parallel is going to be equal to 3 times 3. Because they're in parallel, 3 times 3 over 3 plus 3. So that is going to give us 9 over 6. What is 9 over 6? 9 over 6 is 1.5. So this is 1.5. So this is going to be 1.5 plus the internal resistance, which is 0.5. Total resistance of the lamps in parallel, I've said it is going to be resistance of the lamps total is 3 times 3 over 3 plus 3 day in parallel, which gives us 1.5 ohms. Then it is in series with the internal resistance, that's why I'm adding here plus 0.5. So have 12 divided by 2, which is 6. Then calculate the power dissipated in just one lamp. So power of each lamp, power of each lamp is going to be I squared times the resistance of that lamp. So current is 6. No, current is in the battery. It is going to divide. The current is going to divide. So the current is going to be 3. It will divide equally because these are identical lamps. The current is going to divide equally. So the current is going to be 3 squared. Then times the resistance of each lamp, which is 3. Note how the current is 3. The total current is 6. The current is total current here is 6, but when it reaches here, it divides. So this will be 3, the other one will be 3. Because they're in parallel and they're identical, the current divides equally. So that gives us 9 times 3, which is 27. A third identical lamp is placed in parallel with the battery in the circuit. Describe and explain the effect on the terminal PD of the battery. So we have added another lamp here in parallel. That means total resistance decreases, which means the current flowing increases. That means there will be more lost volts in the battery, and the terminal PD will therefore, the terminal PD will actually be, what do they want? They want PD across the battery. A third identical lamp is placed in parallel with the battery in the circuit. Describe and explain the effect on the terminal PD of the battery. So we have seen that when we add another resistor in parallel, adding the resistances in parallel makes the total resistance to be smaller. So we are saying the circuit resistance is less. Circuit resistance is less, which means more current flows in the circuit. More current flows through the battery What is the effect of more current flowing through the battery? Remember, EMF is equal to terminal PD, that is the PD across the external resistance plus the PD across the internal resistance. So that means the terminal PD is going to be the EMF minus PD across the internal resistance. And the PD across the internal resistance is I times small r. So terminal PD is equal to E minus I times small r. So the circuit resistance is less. That means more current flows through the battery. And if more current flows through the battery, we expect there to be more lost volts. So there are more lost volts. There are more lost volts. There are more lost volts. And if there are more lost volts, if this becomes bigger, remember, E is not changing. IR is becoming bigger, it means the difference is becoming smaller. So there are more lost volts and hence less PD across the battery. Hence less PD across the battery. Hence less PD across the battery. A battery is connected in series with a circuit X, in series with resistors X and Y as shown in the figure. So that is the figure. X and Y is in X and R are in parallel. Then they're in series with Y as shown there. The resistance of X is constant. The resistance of Y is 6 ohms. The battery has EMF 24 and 0 internal resistance. A variable resistor of resistance R is connected in parallel with X. The circuit I from the battery is changed by varying R from 5 to 20. So R is changing from 5 to 20 as shown in that diagram. The current I from the battery is changed by varying R from 5 to 20 and the variation is shown here. Okay. The variation is shown down here. Explain why the PD between points A and C is 24 volts for all values of R. The PD between A and C will always be 24 volts for any value of R. Conservation of energy, total energy would remain 24. And since there is no lost volts, there is no internal resistance, the EMF will always be the total PD across A and C. So that is very simple. There is no energy lost in the internal resistance of the battery. There is no energy lost in the internal resistance. In the internal resistance of the battery. So we don't expect any lost volts. So no lost volts. So there are no lost volts. Therefore, the EMF will always be the PD across SC or the terminal PD. Use the figure to state and explain the variation of the PD across resistor Y as R is increased. We want to state and explain the variation of PD across Y as R increases. Of course, when R is increased, we notice that R is in parallel with X. If R is increased, it means the parallel resistance also becomes greater. If one of those resistors increase, R or X, since we are increasing R, when R increases, it means the PD across the parallel combination is greater. And if the PD across the parallel combination is greater, it means PD across AB becomes higher because V is equal to I times R. PD across AB becomes bigger, which means PD across Y will become smaller. That is very easy. Potential dividers. So we are saying the parallel resistance of X and Y increases. The parallel resistance of X and R increases, which means the PD across AB, PD across the parallel resistors or across AB increases. By conservation of energy, the PD across Y must decrease. So the PD across Y decreases. That is potential dividers. If the PD across the parallel combination increases by conservation of energy, the PD across resistor Y must decrease. So the total is always 24 volts. Then for R equals 6.0 ohms, show that the PD between points A and B is 9 point. Show that the PD between A and B is 9.6 volts. So first of all, we can find the current from the graph at when R is 6.0 ohms. We can check 6.0 ohms. So the scale here is, I think these are 20 small boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So they are 25. So 5 divided by 25, what do we get? 5 over 25, that is 0.2. So the scale on the x-axis is 0.2. So when I count 5 small squares, I will have reached 6 ohms. 1, 2, 3, 4, 5. So 6 ohms is there. So I'll draw a vertical line. 6 ohms is there. I want to see the current when R is 6 ohms. I think the current is here. And what is that current? On the vertical, I think it is the same. 2 minus 1.5. 2 minus 1.5, that is 0.5 divided by 10. No, divided by 25. 0.5 divided by 25, that is 0.025, 0.02. So 0.02 2.4, I mean 2. Okay, I'll just count how many squares. 1, 2, 3, 4, 5. So 5 minus 25, those are 20 small squares. 20 small squares times 0.2, that is 4. So this is 2.4. So the current there is 2.4. So current is equal to 2.4 amperes. So potential difference across AB is going to be equal to the EMF, which is 24, minus the PD across 6 ohms, minus the PD across Y, that is minus PD across Y, which is going to be equal to PD across AB is going to be equal to 24 minus the PD across Y, which is the current, that is the current is 2.4 times the resistance, which is 6 of Y. So that is 24 minus 2.4 times 6, which is 9.6. So that is equal to 9.6. Alternatively, we can find total resistance. Since we have the current, we can find total resistance. Let me use another method, method 2. So total resistance R total is equal to the EMF over total current, which EMF is 24 over the current, which is 2.4. So I think 24 over 2.4 is 10. 24 divided by 2.4 must be 10. So total resistance is 10 ohms. Then I can find resistance across total resistance in parallel. Resistance in parallel, I will get 10 ohms minus 6. So 10 minus 6, which is equal to 4 ohms. That is the resistance in parallel. Then to find the PD across the parallel combination, I'll get the total resistance times the current, that is 4 times 2.4, which is 4 times 2.4, which is 9.6. So it's 9.6 volts. Okay. Then calculate the resistance of X. Calculate the resistance of X. Since we know the resistance of R as 6, we can find the resistance of X. I've even showed you that total resistance is 4 ohms. We can still show that. So now that the P is 9 volts, resistance across AB, or total resistance in parallel, is going to be 9.6 divided by 2.4, which is the total current. And that gives us 4.0 ohms. Now we know that they are in parallel, so 1 over X plus 1 over R should equal to 1 over 4. Or alternatively, I can simply say the product, which is going to be, remember R is 6. So the product is 6 times X over 6 plus X should give us 4. So you just simplify this, you collect like terms. So 6X is equal to 24 plus 4X. So we have that 2X is equal to 24, and it means X is equal to 12, which implies that X is equal to 12. So this is 12 ohms. Alternatively, you can use another method. I'll use a different method. Which method should I use? Okay, I don't have enough space, but I'll use this space here for the second method. So alternatively, I can find the current through R. The current through R is going to be the PD across R is 9.6 because they're in parallel, divided by R, which is 6. And I think that is 1.6. 9.6 divided by 6 is 1.6. That is the current through R. That means I can now find the current through X, which is going to be 2.4 minus 1.6. And that is, I think that is 0.8. 2.4. That is 0.8. Now I can find the resistance X by just looking at the PD over its current. The PD is 9.6 over current 0.8. 9.6 divided by 0.8, which gives us 12. So that would give us 12 ohms. Then calculate the power provided by the battery. Power provided by the battery, that is E times I. Power is equal to E times I. Of course, this is going to be 24 times I, which is 2.4. 24 times 2.4, that is 57.6. You can use another method. You can use power being equal to E squared over R, or you can use I squared times R, any of those methods. If I use E squared over R, it will be 24 squared over R. R is total resistance, which we have got as 10. It is 10. So divide by 10. I think that gives you 57.6. 24 squared divided by total resistance, which is 10, 57.6. State and explain qualitatively how the power provided by the battery changes as the resistance R is increased. Now note that the EMF of the battery is constant, and the power is going to depend on the current flowing through the battery, or it is going to depend on the resistance if the EMF is constant. So I'll begin by noting that the EMF is constant. The EMF is constant, and the power, which method should I use? Should I use current? Okay, let me use V. And the power is going to be equal to 24 squared divided by the resistance. where 24 is the EMF. However, the resistance is going to increase. When R is increased, the resistance is increased, and total resistance increases. Total resistance increases, so the power decreases. Alternatively, you can explain in terms of power is equal to E times I. As R is increased, total resistance increases, the current decreases. If E is constant, the power also decreases. So you can also explain that in terms of E times I, where I decreases as resistance increases, so the power decreases. The IV characteristic of a semiconductor diode is shown in the figure down there. And I think, yeah, it is a diode. The IV characteristic is shown down there. We have seen that earlier on. Use the figure to explain the variation of the resistance of the diode as V increases from 0 to 0.5. Initially, you see that it is a horizontal line, which meant if resistance is equal to V over I, initially V is 0 when there is a current. So it means, no, initially there is V, but when the current is 0, which means resistance is infinite. Initial resistance is infinite. Then after some time, we notice that the resistance decreases because I increases more rapidly than V. So later on, we see that the resistance decreases. Okay, so we are saying resistance is equal to V over I. Resistance is equal to V over I, and there is a very high resistance at low voltages. There is an infinite resistance at low voltages. That's why I said there are values of V, but when the current is 0, that means the resistance is infinite. That is, there is a very high resistance at low voltages, and then the resistance decreases as V increases. And then the resistance decreases as V increases. So there is an infinite, it is infinity. There is an infinite resistance at low voltages, and then the resistance decreases as V increases. You can see that current now increases as V increases, so the resistance decreases. Use the figure to determine the resistance of the diode for a current of 4.4 milliamperes. Current is 4.4 milliamperes. We want to find the resistance of the diode. So we need to get the PD from the graph corresponding to 4.4 milliamperes. So 4.4, the scale here is 2 divided by 5, which I think is 0.4. So 4.4 will be here. And this is going to be 1, 2, 3, 4, 5. So that is 0.5. So the PD is 0.5 from the graph. So PD from the graph equals to 0.50 volts. So we want resistance, which is V over I. That will be 0.50 divided by I, which is 4.4 times 10 power negative 3. 0.5 divided by 4.4 exponent negative 3, which is 113.6 recurring, which is approximately 110. I'll just write 113.6 because I may need to use it later on. Then a cell of EMF 12 volts and negligible internal resistance is connected in series to a semiconductor diode and a resistor R1 as shown in the figure. Resistor R2 of resistance 375 ohms is connected across the cell. The diode has a characteristic shown in the figure 5.1. The current supplied by the cell is 7.6. So the current entering here is 7.6. Of course, here it divides. Part of it takes that route, part of it takes that route. Calculate the current in R2. Of course, R2 is in parallel with the cell, so the PD is 1.2 volts. So that one has no problem. Current is going to be equal to the EMF of V over R, which V is 1.2 and R is 375. So 1.2 divided by 375, that is 3.2 times 10 power negative 3. Then calculate the resistance of R1. So now that we know that the current here is 3.2 milliwatt milliamperes, it means the current here should be 7.6 minus 3.2, which is going to be 4.4. The current there is 4.4 milliamperes. That is the current through the diode, because the sum of currents entering here is 7.6. So it divides into 3.2 and 4.4 milliamperes. So calculate the resistance of R1. Okay, let's find the potential difference across the diode first. Since we know the current flowing through the diode, so I have said I in the diode is 4.4 times 10 power negative 3 amperes. That is the current in the diode. And we can find total resistance across, since we know the resistance of the diode, or we can find the resistance of the diode. We can find total resistance there. So total resistance, that is diode plus R1. Total resistance, which is the resistance of the diode plus resistor R1, is going to be the PD. This part is in parallel, so the PD is 12. It is going to be the PD over the current, which is 4.4. The current through the diode is the same current through R1 because they're in series. So it will be 1.2 divided by 4.4 times 10 power negative 3. And that gives us 1.2 divided by 4.4 exponent negative 3, which gives us 222.7. So this is 272.7 ohms. That is total resistance. However, we have the resistance of the diode above there. For the same diode, the resistance was 113.6, and they're in series, so we subtract. So resistance of R1 is going to be equal to 272.7 minus 113.6, because it's the same diode, so 272.7 minus 113.6. So that gives us 159.1. 159.1 ohms, or approximately 160. So I'll put here 160 ohms. That's, by the way, method 1. Method 2, I could find the PD across the diode and subtract the PD and subtract it from the EMF. Method 2, I could find the PD across the diode correspond to that current is 0.5. We have already seen that before. That means the PD across R1 is going to be 1.2 minus 0.5, which is 0.75. But the current is the same. So resistance is going to be the PD, which is 0.7 divided by the current, which is 4.4 times 10 power negative 3. 0.7 divided by 4.4 exponent negative 3, which is 159.1, which is approximately 160. The ratio, power dissipated in the diode over power dissipated in R2. So we know that power is IV, or we can use I squared R, or you can use V squared over R, depending on what you want, or what is available. I will use the simplest, you can use the rest. So the ratio will be equal to, if I use IV, for the diode, the current is 4.4, its PD is 0.5. For R2, the current was 3.2 milliamperes, its PD was 1.2, the PD of the EMF of the cell. Or I can use I squared, the current is 4.4 squared. The resistance of the diode, we have got it as 113.6 over R2, its current is 3.2 squared milliamperes. Its resistance was 375. Or I can use the last method. The PD across the diode is 0.5 squared times its resistance. No, because here it is dividing, I'm cross multiplying. So I'll multiply by the resistance of R2, which is 375. The current, the PD across R2 was 1.2 but squared times the resistance of the diode, which is 113.6. I'll just press the calculator for one, but I know all the methods, method number 1, number 2, or number 3 will give the same answer. So this will be 4.4 times 0.5 divided by 3.2 times 1.2, which gives us 0.57. So that is 0.57. Okay. The 240 volts power supply S with negligible internal resistance is connected to 4 resistors as shown in the figure. 2 resistors of resistance 550, 950 are connected in series across S. 2 resistors 350R are also connected in series across S. The current supplied by S is 0.4. Current I1 and I2 are shown. Calculate I1. I think I1 is easy. I1 is going to be V over R, where V is the EMF, which will be 240 divided by total resistance, which is 550 plus 950. So that is 550 plus 950. So 240 divided by 550 plus 950, which gives us 0.16. 0.16. Then the resistance R. Now that we know the current coming, we know I1, it means I2 is going to be 0.4 minus that. So I2 is 0.4 minus 0.16, which is equal to 0.4 minus 0.16. So I say 0.4 minus 0.16, which is 0.24. So I2 is 0.24, and we want the resistance R. Since we know the current and we want the resistance R, I think that is very simple. The PD across R and that will be the current times total resistance. So the PD is going to be the current I2 times the total resistance there, and the PD is 240, which will be the current, that is 0.24. Total resistance will be 350 plus R. So I'll just divide 240 divided by 0.24 then minus 350. So R is 650. So R is equal to 650. Then the ratio, power transformed in resistor of resistance 350 over power transformed in resistor of resistance 550. So remember, power can be IV, it can be I squared R, it can be V squared over R. You can use any of those methods. So the ratio is going to be, if I use IV, for 350, the current is 0.24. The PD across 350 is going to be what? The PD across 350, okay, let me use the one which is direct because I don't, okay. V is IR, so this is going to be again 0.24 times R, which is 350, divide by, for the one which is of 550, the current is I1, which is 0.16 times V, which is 0.16 times 550. Okay, so in other words, we have 0.24 squared times 350 divided by 0.16 squared times 550. So that ratio is going to be 1.43. So that is 1.43. You can use any method using any of the quantities given, you'll find the same ratio. 2 points are labeled A and B as shown in the figure 5.1. Calculate the potential difference VAB between A and B. So to find potential difference between between A and B, we may find potential between let me call this point C. Potential between C and B, and we subtract potential between C and A. The difference is going to be we find the potential at B and then the potential at A, and then we subtract. So that will be PD across 350 and PD across 550. We subtract, we just get the highest minus the lowest. So I'll just say PD across 350 is just 0.24, that is the current, times the resistance 350, which is, I think that is 80 something. 350 times 0.24, 84. That is 84 volts. Then I get the PD across 550, which is the current is 0.16 times the resistance 550, which is 0.16 times 550, that is 88. So the PD across this 350 is 84, PD across 550 is 88. So we just get the difference. So it means potential difference between A and B is the difference. Potential AB is going to be 88 minus 84, which gives us 4.0. So the answer there is 4.0 volts. Alternatively, we can also find the PD across R. Remember, we have found R to be 650. So I'll do this method from here. I'll find the PD across 950, which is equal to the current is I1. I1 is 0.16 times 950. 0.16 times 950, that is 152 volts. Then I get the PD across R, which is 650. The current there was I2, which was 0.24 times R, which is 650, and that gives us 0.24 times 650, which is 156 volts. So we now get the difference. Potential difference AB is the difference between those two values, 156 minus 152, which gives us 4.0 volts. So that will be another way of arriving at the same answer. Then the resistance R is increased. State and explain the effect on VAB. The resistance R is increased. Let's just look at the method where we used R as the resistance, as the PD across 550. R was 550. If 550 is increased, it means the PD across R is going to be greater. The PD across R is going to be greater. And if the PD across 950 does not change, and yet the PD across R has increased, it means the PD across AB, the difference here is going to be greater. If this is increased, the product is going to be a greater value. When we subtract, we shall get a value greater than 4.0 volts. So the PD across AB increases. Okay, so we shall just put that in writing. Because the PD across AB is going to be the PD across R minus the PD across 950 ohms. If R is increased, it means PD across R increases. That means the difference becomes bigger. So we are saying the PD across R increases, or you would say the PD at B, potential at B increases, or potential at B increases, or potential at B increases. Hence, VAB increases. Alternatively, you could say potential across, if the PD across R increases, it means the PD across 350 decreases. And still, if the PD across 350 decreases, remember we got potential difference also from PD across AB was equal to PD across 550 minus the PD across 350. If the PD across 350 decreases, then the difference is again bigger. So we can say, oh, you say the PD across 350 ohms decreases. So VAB increases. Okay, so the PD across AB increases in any case. A 12 volts battery with internal resistance 0.5 is connected to two identical filament lamps L1 and L2 as shown in the figure. The lamps are connected to the battery via switches S1 and S2. The power rating of each lamp is 48 watts, 12 volts. S1 is closed and S2 is open. So S1 is closed, S2 is open. State and explain whether the power transformed in L1 is 48 watts. Because there is an internal resistance, the power transformed is going to be less than 48 watts. Some energy is dissipated within the battery, so they are lost volts. So we are saying the internal energy causes, or the internal resistance, the internal resistance causes lost volts. Causes lost volts within the battery. So the PD across the lamp is less than 12 volts. The PD across the lamp is less than 12 volts, and therefore the power is less than 48 watts. The power is less than 48 watts because the PD across the lamp is less than 12 volts. Then S2 is now closed, so they are now both closed. State and explain the effect on the current in L1. So since the S2 is also closed, there are now two bulbs in parallel. There's going to be this time the current flowing is going to be reduced. The current flowing through the battery is going to be reduced. Remember the lost volts. Lost volts is going to be the current times internal resistance. If the total resistance here becomes small, it means the current flowing through the battery is going to be greater. Because connecting the two bulbs in a cell in parallel reduces the total resistance. So the current becomes greater, that means the lost volts increase. But remember the PD across the bulbs is going to be the EMF minus the lost volts. So the lost volts becomes greater, that means the PD across the lamps becomes smaller. And if the PD across the lamps becomes small, it means there will be actually less current in the lamps themselves. So we are saying there is now greater lost volts. There is now greater lost volts. Or you can say the PD across the cell or the lamp is reduced. Or the PD across the lamp is reduced because that is the terminal PD. And it is the PD across the cells, the terminals of the cell is reduced. And if the PD across the terminals of the cells is reduced, if the lamps have whatever resistance they have, we expect that the current, if we keep R constant, we expect that the current in the lamp is less. So there is thus less current in the lamp. Thus less current in, thus less current in the lamp. Thus less current in the lamp. So because the PD is equal to EMF minus the lost volts, there is a greater lost volts, so the PD across the lamp is smaller, so we expect a smaller current in the lamps. Then state and explain the effect on the resistance of L1. So now that there is a smaller current in the lamp L1, then how about the resistance? Since the current is smaller, or since the PD has become smaller, then if resistance is equal to V over I, if the PD has become smaller, then it means the resistance is going to be smaller. So the PD across the lamp is or decreases, hence the resistance decreases. The PD across the lamp decreases, hence the resistance decreases. So the resistance decreases because now the PD across the lamps will be due to the total resistance which has become smaller. So it also means that the resistance of the lamp L1 naturally decreases because the PD across the lamp becomes smaller. Sketch the temperature characteristic of a thermistor. So we know that a thermistor has its resistance decrease as temperature increases. So we are going to have a characteristic graph which has a decreasing gradient, but should never touch the x-axis. So that should be the shape of the curve. It should never touch the x-axis, but with a decreasing gradient. So yours should be a smooth graph, better than mine. A potential divider circuit is shown in the figure 5.2. Let's look at figure 5.2. Battery of EMF 12 volts and negligible internal resistance is connected in series with X and Y and the thermistor Z. The resistance of Y is 15 kilo ohms, so this is 15 kilo ohms. And the resistance of Z at particular temperature is 3 kilo ohms. This is at a particular temperature. The PD across Y is 80 volts. Explain why the power transformed in the battery equals the total power transformed in Y, X, Y, and Z. Look at the graph, the diagram, and note that there is negligible internal resistance. So if there is negligible internal resistance, it means no energy is lost in the battery. Therefore, the power transformed in the battery will always be equal to the total power transformed in X, Y, and Z. So we simply say, I'll reduce the thickness. No energy lost in the battery. No energy lost in the battery because of negligible internal resistance. Negligible internal resistance. Then calculate the current in the circuit. Of course, current is equal to V over R. V is, they gave us the potential difference across Y is 80 volts. They have given us its resistance. When V is 80 volts, the resistance is 15 kilo ohms. We can use that to find the current. So this will be 8 divided by 15 kilo ohms. That's 15 times 10 power 3. So that would be 8 divided by 15 exponent 3. So that is 5.3 times 10 power negative, is it negative 4? So that is 5.3 times 10 power negative 4. Alternatively, they gave us, let me check. Yeah, I think that is enough. The other methods would be longer. Find the PD across Z, finding the PD across X would actually take us longer time. But I think this is fine. 5.3 times 10 power negative 4 amperes. Then calculate the resistance of X. So the current is the same because they're in series. So we now have the current, and they have told us at a particular temperature Z has 3 kilo ohms, and the current is that. So we can find the resistance of X. So current is equal to EMF over total resistance. The current is 5.3 times 10 power negative 4 is equal to the EMF, which is 12, divided by total resistance, which will be resistance of X. It will be resistance of X plus 15 times 10 power 3. That is for what? 15 times 10 power 3 for y, then plus 3 times 10 power 3 for z. So it means I will just make r the subject in the calculator. So I'll say 12 divided by the answer, which is that, minus, open brackets, 15 exponent 3, okay, I'll just first do that, minus again 3 exponent 3, which is 4,500. So this is 4,500 ohms. So I just used I is total current is equal to EMF over total resistance. Total resistance, they are in series, so I just sum them up. Alternatively, you could find the PD across Z by finding, across X by finding the PD across each of these. This is 8. The PD here will be 3 times 10 power 3 times the current, which is 5 times 0.3 times 10 power negative 4. That will be the PD across there. So the sum of this PD and this one, we subtract from 8. We get the PD across X. So the PD across X is equal to the current, which is 5 times 0.3 times 10 power negative 3 times the resistance across X. That is the PD across X. And it should be equal to 12 minus 8 plus 3 times 10 power 3 times 5.3 times 10 power negative 4. So I can check this again. So I'll say 12. Okay, let me start with the bracket. 3 exponent 3 times 5.3 exponent negative 4. That is it, plus 8. That's what you get. 12 minus the answer. That's what you get. Then divide by, open brackets, 5.3 exponent negative 3, which gives us 4. No, this is negative 4. So that gives us that gives us 455.40, which is approximately 4,500. There's just a typing error there, but is 4,500. You can check. Okay. So the temperature of Z is increased. Temperature of Z is increased. Of course, Z is the thermistor. When temperature increases, resistance decreases. That means the PD across the thermistor decreases. So the PD across the other resistors should be increasing. State and explain the effect on the potential difference across Z. Of course, it decreases. So resistance of Z is going to decrease, and the PD across Z is Rz over Rx plus Ry plus Rz, then times V. So if Z decreases, it means the PD across Z decreases. So we are saying resistance decreases, resistance of Z decreases. Hence the current in the circuit is greater. The current in the circuit is going to be greater, but the PD across Z decreases, or the PD across X and Y are going to be greater. So PD across Z decreases as PD across X and Y becomes greater or increases. A battery of EMF 6 volts and negligible internal resistance is connected to 3 resistors, each of resistance 2.0 kilo ohms, and the thermistor as shown in the diagram. The thermistor has resistance 2.8 kilo ohms at 10 degrees Celsius and 1.8 at 20 degrees Celsius. Calculate the potential at point A. So to find the potential at point A, I will find the potential difference between A and the earth, because at earth the potential is 0. So the potential difference here will be the potential at A. So potential at A will be equal to the resistance. There I'm using potential dividers. The resistance is 2.0 kilo ohms divided by total resistance, which is 2 plus 2, that is 4 kilo ohms, times the voltage supply, which is 6. That is a potential divider. V out is equal to R1 over R1 plus R2 times V supply. That is for the potential divider. So this is going to be equal to 6 over 2, which I think is 3.0 volts. Kilo has cancelled. So that is 3.0 volts. Then at point B, for the thermistor at 10 degrees Celsius. So we want at point B, for the thermistor at 10 degrees Celsius, the thermistor has a resistance of 2.8 kilo ohms. So total resistance is 2.0 plus 2.8. Therefore, the potential at point B is going to be 2.0 divided by 2.0 plus 2.8. Remember, these are in kilo. Then times the voltage supply, which is 2 divided by 4.8 times 6, which is 2.5. So this is 2.5. Then at point B, for a thermistor at 20 degrees Celsius. So at 20, R is 1.8. So again, potential at B is going to be the resistance, which is 2 divided by total resistance is 1.8 plus 2.0. We are always considering the resistance because we want potential at B. Potential at this end is 0, so potential at B will be the potential difference between B and the earth, where the resistor there is just 2 kilo ohms. So this will be 2 over that. Remember, these are in kilo, so kilo cancels, then times 6.0. So we have 2 divided by 3.8, then times 6, which is 3.2. A student designs the circuit of the figure to detect changes in temperature in the range 0 to 100 degrees Celsius. The resistance of the thermistor RT and that of the resistor R is R. The student monitors the potential difference V out. State and explain whether V out increases or decreases as the temperature of the thermistor increases. So as the temperature increases, as temperature of the thermistor increases, RT decreases. As RT decreases, it means PD across RT becomes smaller, which means the PD across R becomes greater, so V out increases. Okay, so we just say resistance of the thermistor, decreases as temperature increases. Resistance of the thermistor decreases as temperature increases, but not V out is going to be R over R plus RT, then times V. So V out increases. So V out increases. Because RT decreases, it means even if I divide R over R plus RT, I get a relatively larger value than before when RT is smaller. So V out becomes bigger. So V out increases. Then whether the change in V out varies linearly with the change in temperature of the thermistor. It doesn't, because Resistance does not vary perfectly linearly with the temperature. Therefore, V out does not also vary linearly with the temperature. We saw that for a thermistor, it was a curve like that. So resistance of a thermistor does not vary linearly with the temperature. So the change in V out is also nonlinear. So the change in V out is also going to be nonlinear because the resistance does not vary linearly with the temperature. The strain in a beam is to be monitored using a strain gauge. The strain gauge is included in the potential divider circuit shown in the figure down here. Okay. The strain gauge has resistance 120 ohms when it is not strained. The resistance increases to 121.5 when the strain is epsilon. Calculate the potential difference between points A and B on the figure when the strain in the gauge is epsilon. So we want the potential difference between A and B. So we need to find the potential at A and then the potential at B. Then we subtract. So potential at A, the strain gauge, when it is strained, has resistance 121. So we are using the formula for potential divider. V out is equal to R1 over product of sum of the resistances in that branch of the potential dividers times voltage supply. So VA is going to be when the strain gauge is strained, this is 121.5. So we shall say 121.5 over total resistance, which is 121.5 plus 120. That is 121.5 plus 120. Then times the voltage supply, which is 2000 millivolts. So that will be times 2000 millivolts. 121.5 divided by the sum of 121.5 and 120 times 2000. So that is 1006.2. 1006.2 millivolts. Then we can check potential at point B. So with the resistor there is 5000, so we have 5000 divided by total resistance, which is 5000 plus 5000. It is 5000 plus 5000, then the potential across them is 2000. So in other words, we have 5000 over 10,000. So that is 2000 times a half, or 2000 divided by 2, which is 1000 millivolts. So now we want the potential difference between A and B, so we just subtract. So potential difference between A and B is going to be 1006.2 minus 1000. So 1006.2 minus 1000, which is 6.2 millivolts. This is still in millivolts. State Kirchhoff's first law. We have been stating it as sum of currents into a junction equals sum of currents out of the junction. So I'll just say algebraic sum. Algebraic sum of currents at a junction is 0. The algebraic sum of currents at a junction is 0. Or you can lose, let's say, the sum of currents into a junction is equal to the sum of currents out of the junction. A battery of EMF 120 volts and internal resistance R is connected to a filament lamp and a resistor as shown here. So that is the diagram. We can look at it. So we can even predict that the current here is going to be 3.6 minus 1.2, which is going to be 1.4 amperes. Okay. The current in the battery is 3.6 and the current in the resistor is 2.1. The IV characteristic of the lamp is shown there. So determine the resistance of the lamp in the figure. So if first of all we have seen the current of the lamp, the current through the lamp is equal to 3.6 minus 2.1 using Kirchhoff's first law. And that is, no, it is not, did I say 2.1.4? It is 1.5. This is 1.5, not 1.4, because this is 2.1. Yeah, I saw it as 1.2 because, so this is 1.5 amperes. So the current, that is 1.5 amperes. Let's check on the graph what is 1.5 amperes in terms of PD. So 1.5 is here and the PD is here. The scale on the vertical is 2 over 10, 0.2, so this is 4.4. Therefore, the PD across the lamp, the PD of the lamp is equal to 4.4 volts. So that is 4.4 volts. So now resistance is going to be V over I, which is 4.4 divided by I, which is 1.5. 4.4 divided by 1.5, which is 2.9. 2.9 ohms. Determine the internal resistance R of the battery. Determine the internal resistance R of the battery. So to determine the internal resistance of the battery, we need to find the terminal. We can find the terminal PD, and the terminal PD, because the PD across the lamp is the same as the PD across the other fixed resistor, which we have seen as 4.4. That means we can easily find the terminal, the lost volts. Can easily find the lost volts. So I will simply say the PD across the lamp is the same as the PD across the other resistor, which is the same as the terminal PD. And we have seen that it is 4.4 volts from the graph. Therefore, the EMF is equal to the terminal PD plus the lost volts, VR. The EMF is 12 volts and the terminal PD is 4.4 plus the lost volts. Note that VR is equal to I times small r. The lost volts is going to be the current, which current is the current through the battery is 3.6 times the internal resistance R. So just press our calculator and find our answer. So it is 12 minus 4.4 divide by 3.6. Sorry, 12 minus 4.4 divide by 3.6, which is 19 over 9, which is 2.1. So the internal resistance is 2.1. Then the initial energy stored in the battery is 470 kilojoules. Assume that the EMF and the current in the battery do not change with time. Calculate the time taken for the energy stored in the battery to become 240 kilojoules. So we know that energy is equal to power times time. That is electric energy, which is power is IV times time. So they are telling us to calculate the time taken for the energy stored in the battery to become 240 joules. So there is a change in energy. So the time t is going to be equal to change in energy divided by I times V. So energy changes from 470 to 240. So this will be 470 times 10 power 3 minus 240 times 10 power 3. That is the change in energy over IV. And the current was 3.6 in the battery and V is 12 volts. That's the EMF. So we have 470 exponent 3 minus 240 exponent 3 divided by 3.6 times 12, which is 5324. 5324 seconds, which is approximately 5300 seconds. Then the filament wire of the lamp is connected in series with the adjacent copper connecting wire of the circuit as illustrated in the figure. So they have given us the diagram there. They have given us for the filament wire cross-sectional area, number density of free electrons. They have given us the cross-sectional area for the copper wire and the number density of free electrons. Calculate the ratio average drift speed of free electrons, the filament wire over average drift speed of free electrons in the copper wire. So we already know that drift speed V is equal to current divided by N cross-sectional area times the charge of the electrons. So we want now the ratio. The current is the same because they're in series, so I'll say I. I'm looking at the filament wire first. So that will be I over N, the number of free electrons per unit volume. Then the area is A, then times E, divided by for copper wire. The current is the same I over N is going to be 2.5 N. Area is going to be 360 times A, then times E. So the ratio is going to be equal to I over NAE times reciprocal 2.5 N times 360 A times E divided by I. And I just want to show that I cancels, N cancels, A cancels, E cancels. So you remain with the 2.5 times 360. 2.5 times 360, that is 900. Then state Kirchhoff's second law. We have stated this several times. At this point, you should now be familiar with it. The algebraic sum of EMFs and PDs is zero around a closed circuit. Algebraic sum of EMFs and PDs is zero around a closed circuit. or a closed loop. Alternatively, you can simply say the sum of EMFs. You don't need to write EMF in full, just write EMFs. The sum of EMFs is equal to the sum of PDs around a loop. So that is Kirchhoff's second law. A battery has EMF 4.0 volts, internal resistance is 0.35. The battery is connected to a uniform resistance wire XY and a fixed resistor of resistance R as shown in the figure here. Wire X has resistance 0.9, wire XY has resistance 0.9 ohms. The potential difference across XY is 1.8 volts. So PD across XY is 1.8 volts. Calculate the current in wire XY. So our current is equal to the PD divided by the resistance. PD is 1.8, resistance is 0.90. I think that is just twice. 1.8 divided by 0.9, I think that is 2. So that will be 2.0. Calculate the number of free electrons that pass a point in the battery in a time of 45 seconds. Number of free electrons. We know that total charge is number of electrons times the charge of each electron, which is current times time. So we want N. Number of electrons will be current times time divided by the charge of each electron. The current is 2.0, the time is 45 seconds, divided by 1.6 times 10 power negative 19. So 2 times 45 divided by 1.6 exponent negative 19. So that is 5.6 times 10 power 20. 5.6 times 10 power 20. Then our resistance R. We want now to find resistance R. So the current through the wire is the same as the current through the resistance R. Therefore, if I use a simple formula such as total current I is equal to the EMF divided by total resistance R total. The total current is 2 amperes. 2.0 is equal to the EMF, which is 4, divided by total resistance, starting with the internal resistance 0.35 plus the resistance of the wire, which was given as 0.9 plus the resistance of R, which is just R. So this is going to give us R easily. So I'll just I will just cross multiply, or I will simply say 0.35 plus 0.9, that is 1.25. So 1.25 plus R is equal to 4 divided by 2, which is 2. So R is going to be 2 minus 1.25. 2 minus 1.25, which is 0.75. So R is 0.75. Alternatively, you can find the PD across the wire. You also find the PD across the internal resistance, and you subtract it from 4. You find the PD across R. Then you divide by the current. That is, I'll take you back here so that I use this space. So if I want the PD across R, which is current times R, is going to be the EMF, which is 4, minus the PD across the rest. That is minus 1.8 for the wire, and then plus 0.35 times 2, because the current is 2. So I, which is 2 times R, is equal to, so this is 4 minus what is in the bracket. So I will say 4 minus, in the brackets I have 1.8 plus 0.35 times 2, which is 1.5. So this is 1.5. then divide by 2, which is 0.5. So R is 0.75. Okay. A cell of EMF 12 volts is connected to the circuit in B as shown in the figure. Okay. The connection P is moved along the wire XY. The galvanometer reading is 0 when XP is 0.3. So when XP is 0.30 meters, remember the length of the wire. Okay, the length was not really given. It's what we want to find. The length of the wire is what we want to find. So calculate the total length L of the wire. So first of all, the PD across the wire was 1.8. PD across XY was 1.8 volts. So we can find a PD per meter. Let me call it PD per unit length. PD per unit length is going to be 1.8 divided by total length L. That is the PD per unit length. Remember, resistance is directly proportional to length. Resistance is directly proportional to length. And the PD across XP is going to be the EMF of the cell for balance. So PD across XP is going to be equal to 1.2 volts. But what is that PD? The PD across XP, which is 1.2 volts, can also be 0 because PD is going to, we have the PD per unit length as 1.8 over L. So the PD across XP will be the length, which is 0.30 times the PD per unit length, which is 1.8 divided by L. So this is volts, this was volts per meter, and now this is going to be volts. Okay, so 1.2 is equal to that, so we can now find L. So L is going to be 0.30 times 1.8 divided by 1.2. I have said that for balance, PD across XP is the same as the EMF because they are in parallel. That part XP is in parallel with the cell, so they are the same. So we just press our calculator, 0.3 times 1.8 divided by 1.2, which is 9 over 20, and 9 over 20 is 0.45, so that is 0.45. The fixed resistor is replaced by a variable resistor of resistance greater than R. State and explain the change, if any, that must be made to the position of P on the wire XY so that the galvanometer reading is 0. So we have simply seen that the PD across XY over the PD across XP is directly proportional to the length XY over the length XP. So the fixed resistor is replaced by a different fixed resistor of resistance greater than R. What does that mean? The PD across R is greater, which means that the PD across XY is greater. So the PD across this one, R is greater, which makes the PD across XY smaller. That's one. So that means XY is smaller. So I'm saying the PD across R is greater because PD is equal to I times R. So the PD, because R has increased, the PD across R is now greater. So if that is greater, it means for the wire it reduces because they're in series. So the PD across X, Y decreases. So we have seen that this Vxy is becoming smaller. Vxy is becoming smaller, but remember length xy is constant. What we can vary is Vxp, which is directly proportional to Lxp. But because this is smaller, then Vxp is going to be smaller. But we want, if state and explain the change, if any, that must be made to the position of P in the wire XY so that the galvanometer reading is 0 again. So it means Since Vxy has reduced yet Lxy is not changing, by all means we must increase Lxp to make Vxp increase so that there is a balance. Therefore, P must be moved so that Lxp increases. So P is moved towards Y to increase the length xp, because if xp does not increase, then the right hand side of the equation will not be balancing with the left hand side, since Lxy is not going to change. Okay. Define the ohm. The ohm, we said resistance is V over I. This is resistance is in ohms, V is in volts, and I is in amperes. So the ohm can be defined as volt per ampere. A wire is made of a metal of resistivity ρ and length L of the wire. The length L of the wire is gradually increased. Assume that the volume V of the wire remains constant as its length is increased. Show that the resistance R of the extending wire is proportional to L squared. So we know that resistance is equal to rho L over area. And we know that area is equal to volume over length, because volume, area times L is volume. So area is going to be volume V over L. So it means the resistance is going to be rho L divided by volume over L, which is rho L over 1 times L over V. So resistance is going to be rho L squared over V. But remember, rho is constant and V is constant. So since rho and V are constant, rho and the volume are constant, then R is directly proportional to L squared as required. A battery of EMF E and internal resistance R is connected to a variable resistor of resistance R as shown in the diagram. An ammeter measures the current I in the circuit. A voltmeter measures the potential difference V across the variable resistor. Okay. The resistance R is now varied. To change the values of I and V, the variation of I of V is shown here. Use the figure to state the EMF E of the battery. We know that EMF is equal to the terminal PD. When I write capital V subscript capital R, it means terminal PD, plus capital V subscript small r, that is the lost volts. So the EMF is equal to VR terminal PD plus lost volts. Maybe let me write it here. EMF is equal to terminal PD V plus the lost volts, which lost volts is I times small r. So state the EMF E of the battery. So EMF is going to be the terminal PD V R plus I times R. So when there is no current flowing through the battery, it means the internal the lost volts is 0. That means for I equals to 0, then EMF is equal to terminal PD, which in this case from the graph, it is 2.1234, that is 2.4. So from the graph, that would be 2.4. So the EMF is 2.4. Again, use the figure 5.2 to determine the power dissipated in the variable resistor when there is a current of 5 amperes. So 5 amperes 5 amperes. I'm looking for 5. 1, 2, 3, 4, 5. That is 5 amperes. And 5 amperes corresponds to 1.3. So this is 1.3 volts. So the power, we know that power is equal to I squared R, or power is equal to, since we have I and V, so power can be IV, or power can be V squared over R. So I'll use IV. So power is going to be I, which I is 5.0 times, and it is squared. No, I'm using IV. So I'll just say 5.0 because I don't have the current, the resistance yet. So that is 5. I'm using power is equal to IV, which is 5 times, the current is 5 times V, which is 1.3 from the graph. 5 times 1.3, which is 6.5. So this is 6.5. You can also look for the resistance and find power from V squared equals to power from I squared R or V squared over R, but that will be a long process. Finding the resistance, state what is represented by the value of the gradient of the graph. We can find out. It is a graph of V against I, so I will make V the subject. Terminal PD is equal to the EMF minus I times R. It is a graph of, compare with Y is equal to mx, so this will be C plus mx. On the y-axis we have V, on the x-axis we have I, so the gradient is negative R. So the gradient is negative R, so that is negative internal resistance, negative internal resistance. Define EMF. We have said EMF is the energy transferred from other forms such as chemical to electrical per unit charge. Energy transferred. I think that is double R. Energy transferred from other forms such as chemical to electrical per unit charge. Energy transferred from other forms such as chemical to electrical per unit charge. The circuit shown in the figure contains a battery of EMF E that has internal resistance R, a variable resistor, a voltmeter, and an ammeter. Readings from the two meters are taken for different settings of the variable resistor. The variation with the current I of the potential difference V across the terminals X, Y of the battery is shown in the figure here. So that is a graph of V against I. Explain why V is not constant. I hope there is internal resistance. Yes, since there is internal resistance, there is a PD, there must be a PD across the internal resistance, and that PD increases with the current. And from the expression, our terminal PD is equal to EMF minus I times R. If the current increases, it means if the EMF is not changing, then the terminal PD must be decreasing because the lost volts increase. So we are saying there is a PD across. There is a PD across the internal resistance. and that PD is current times small r. There's a PD across the internal resistance. So a change in current is going to result into a change in PD across the internal resistance. A change in current results in a change in PD across the internal resistance. So a change in current is going to result into a change in PD across the internal resistance. And we have seen that V is equal to E minus the PD across the internal resistance. So it means, so I'll just say V equals the EMF minus the PD minus the PD across internal resistance. So it changes. So it changes. So V must change. The PD and terminal PD must change. Okay. For the battery in B, use the figure to determine the EMF. So we have seen that the terminal PDVR the terminal PD is equal to the EMF minus the lost volts. And when I is equal to 0, when there is no current flowing through the battery, it means the EMF is equal to the terminal PD. So we just look for the terminal PD from the graph when the current is 0. So when the current is 0, the PD is, we have to prolong this upwards. We shall prolong the line. We must take this line backwards. Hope I've tried to make it clear, correct. Maybe you can draw a better line than mine. Just prolong that line upwards. Maybe I can increase the thickness. Okay, so that is my line. And I think it is stopping at 7 point something. Let me check. 7 point what? So the scale on the x-axis is 0.2, 2 over 10, 0.2. So this is going to be 1, 2, 3, 4, 5. That is 7.2.4. 7.4. So the EMF is 7.4 when the current is 0. So this is 7.4, which is 7.4 volts. So that is 7.4. Then the maximum current that the battery can supply. The maximum current that the battery can supply. So that's why I took the graph to the x-axis. So the maximum current when the EMF becomes, when the battery completely dries out, that is when the PD is 0, what is the maximum current? When V equals to 0, it means E is equal to I times R. So this is going to give us the maximum current. So we look for the maximum current. I think it is at this point here. Let's check. The x-axis, the scale is 0.02. So 1, 2, 3, 4, 5, 6. 6 times 0.02 plus 0.8. That is 0.92. So the maximum current is maximum current is equal to 0.92 amperes. That is when V becomes 0. Then the internal resistance, so since we have that for maximum current, V is going to be 0. That means R is going to be E over the maximum current. So from V equals to E minus IR at maximum current, V is equal to 0, which means IR is equal to E, which means R is going to be E over I max. And we have seen that EMF is 7.4 and I max is 0.92. 7.4 divided by 0.92, that gives us 8.004. 8.04 ohms. Alternatively, we note that we can use the gradient, because we know that the gradient of the graph, if we compare with y is equal to mx, the gradient of the graph is equal to negative r. So let's find the gradient. I'll take points from the line which was originally drawn. So I'll take this point 1, 2, 3, 4, 5. I'll take this point 5. 5 corresponds to, that is 0.3, and I'll also take this point which is 2 point. This point here which is 2.4, and 2.4 corresponds to 0.62, that is 0.62. So I'll find the gradient. So method 2, I'm using the gradient, so I'll say 2.4 on the vertical axis, 2.4 minus 5.0 is going to be 0.62 minus 0.3, which is equal to negative r. So we have 2.4 minus 5 divided by 0.62 minus 0.3. That is negative 8.1. The negative cancels. So we have negative 8.125 equaling to negative r. So r is equal to 8.1. So I'll write here 8.1. That's quite a bit. Internal resistance. On the figure, sketch the line to show a possible variation with I for the battery with the lower EMF. That means the graph should be below the graph that we have there, and a lower internal resistance than the battery in B. Your line should extend over at least the same range of currents, as the original. So, of course, if it extends over the same range of currents, so the graph is going to be below the one that we have there. Remember, V is equal to E minus I times R. First of all, I will choose a value lower than that one for the EMF. Let me choose this value here for the EMF. My graph starts from there. Number 2, what will happen to the gradient? Let's also verify the maximum current. Suppose I have chosen 4 as my EMF. When V is 0, the EMF is 4 minus the maximum current I times, because they told us the circuit contains, sketch the line to show the possible variation with I of a battery with a lower EMF. So the EMF is lower, and a lower internal resistance. So R is going to be smaller. Remember, the maximum current is equal to EMF divided by R. Maximum current is going to be EMF over R. So R is smaller and E is also smaller. So it means the maximum current is also going to be a smaller value. Therefore, I will draw a line which does not reach 0.92. So I will draw a new graph. I will use a different color for that line. Let me use red. So its gradient is going to be less than the one that we had before. So I will draw it here. So that is going to be my graph. First of all, it is less steeper than the previous one. It is a straight line with a negative gradient, but the gradient is smaller in magnitude than the original line. The line has an intercept on a value of on the y-axis below the original value below the original line that we had, because it was of a smaller EMF. Okay, so that would be our new graph. They say we label the line? No. Okay, state Kirchhoff's first law. State Kirchhoff's first law. So now we know Kirchhoff's first law. The algebraic sum of currents is 0 at a junction. The algebraic sum of currents is 0 at a junction. You must mention the junction. Or you will lose, let's say, okay, at a junction in a circuit. Or you will lose, let's say, that the sum of currents in a junction or into a junction equals the sum of currents out of a junction. In a circuit. Okay, the circuit shown in the figure contains a battery of EMF E, a negligible internal resistance C connected to 4 resistors R1, R2, R3, and R4, each of resistance R. So each of these has resistance R. They are all identical. So the current here is 0.3, but they are identical, yet the potential difference across them is going to be the same. It doesn't require to be a genius to predict that the current here will also be 0.30. They are identical resistors. They are in parallel. It means the current which comes here is being divided equally. That means I now know the current through the battery. The current through the battery will be 0.30 plus 0.30, which is 0.60. That is the current which reaches here and is divided into, okay? So the current in R3 is 0.3, the PD across R4 is 2.4. Show that R is equal to 4.0 ohms. So we now know the current through R4. Because R4 is in series with the battery, so the current flowing through it is the current I've just obtained here. So I'll simply say that current in R4 is going to be equal to, is the same as, by the way, is the same as current in R1, which is going to be 0.30 plus 0.30, which is equal to 0.60 amperes. I've used Kirchhoff's first law. That is the current. So we have the PD. Now it is just about finding the resistance as V over I, which is 2.4 divided by 0.60, 2.4 divided by 0.6, which is 4.0 ohms. Determine the EMF of the battery. So to determine the EMF by conservation of energy, the EMF of the battery should be equal to the total PD outside there, total PD. So it will be the PD across the parallel combination plus the PD across R1 plus the PD across R2. So if the battery has no internal resistance, the EMF should be the terminal PD. So this will be PD across R1 plus PD across R4 plus the PD across the parallel combination. So PD across R1, we have seen R1 is, the resistance R is 4. So R1 is 4 times the current is 0.6 plus the PD across R4 is 2.4. We don't need again to multiply, plus the PD across the parallel combination will be the total current entering the parallel combination is the total current entering the parallel combination, or I can even just use one resistor. One resistor has resistance 4 and the current that the PD across each is the same. So if this is 4 and this is 0.3, the PD across them is just as good as taking the PD across one resistor, which will be simply 0.3 times 4. You don't need to do for the second resistor because it is the same. So it will be 4 times 0.6 plus 2.4 plus 0.3 times 4, which gives us 6.0. So the EMF is going to be 6.0 volts. 6.0 volts. The battery in B is replaced with another battery of the same EMF but with an internal resistance that is not negligible. State and explain the change, if any. State and explain the change, if any, in the total power produced by the battery. The battery is replaced with another battery of the same EMF, but this time it has an internal resistance that is not negligible. State and explain the change, if any, in the total power produced by the battery. So now, since the internal resistance is not negligible, it means the resistance has increased. So the current flowing through the battery is smaller. And since power produced is equal to E times the current, it means the power is going to be smaller. So we are saying total resistance increases. Total resistance increases, which means the current through the battery decreases. The current decreases, the current through the battery decreases, and since power produced by the battery is E times I, so the total power decreases. So total power decreases. The resistors in the circuit of the figure 5.1 are made from nichrome wire of uniform radius, 240 micrometers. The length of the wire needed to make each resistor is 0.64 meters. Remember, there are 4 resistors. Calculate the resistivity of nichrome. So we know that resistance is equal to rho L over M, and we want to find resistivity, which will be R times A divided by L. And they have given us the radius, so this time area will be equal to pi r squared. not pi d squared over 4. So the resistance of, remember the resistance of the wire was 4 ohms, so this is 4.0 times the area, which is pi, times the radius, which is 240. It is micro, so that will be times 10 power negative 6, and this is going to be squared, divided by the length, which is 0.67. So 4 times pi times open brackets 240 exponent negative 6, and this is squared, divided by 0.67. So that is 1.08 times 10 power negative 6, or 1.1 times 10 power negative 6 ohm meters. A cell of EMF 0.48 volts is connected to a metal wire X as shown in the figure. The cell has internal resistance. The current in the cell is 0.8 amperes. Wire X has length 3 meters, cross-sectional area 1.3 times 10 power negative 7, and resistance is 0.4 ohms. Calculate the charge passing through the cell in a time of 7.5. So we know that charge is equal to IT. The current is 0.8. The time is 7.5 minutes times 60 to change it to seconds. So 0.8 times 7.5 times 60, that is 360. Calculate the percentage efficiency with which the cell supplies power to wire X. Percentage efficiency with which the cell supplies power to wire X. So efficiency is going to be power in output over power input. So efficiency is going to be power out, which goes to wire X, over power input, which is produced by the battery. So this is going to be I times V divided by I times EMF. So I times V, the current is 0, the current cancels out. We just need the PD outside, the terminal PD. And the terminal PD is again current times resistance. Wire X has length of 3 meters. This, I'm looking for the PD across wire X. The charge that passes through the cell is that the resistance of wire X is 0.4 ohms and the current passing through it is 0.8. So the PD, this is going to be, by the way, I squared R divided by I squared, okay, divided by I times E, because we have the EMF. So this will be, the current is 0.8. I'll just square 0.8 squared times the resistance, which is 0.4, that is for wire X, divided by the current, which is 0.8, times the EMF, which is 0.48. So 0.8 squared times 0.4 divided by 0.8 times 0.48. So that is giving us 0.66. They want the answer as a percentage, so times 100. So we multiply this by 100. So that gives us 66.6 recurring, which is 67%. There are 3.2 times 10 power 22 free electrons contained in the volume of wire X. For wire X, calculate the number density N of the free electrons. So we know that current is equal to never. So we want the number density of free electrons. Of course, they have given us the number of electrons contained in a volume of X. Number density is number of charge carriers per unit volume. So we have 3.2 times 10 power 22 divided by the volume. Remember, volume is cross-sectional area times length. The cross-sectional area is this one, the length is 3 meters. So volume, V is not volume, that is drift speed. Volume is equal to the cross-sectional area times length. So the cross-sectional area was given as 1.3 times 10 power negative 7, then times the length, which is 3. So 3.2 exponent 23 divided by 1.3 exponent negative 7. I will start with 3. 3 times 1.3 exponent negative 7, which is 8.2 times 10 power. Sorry, this one is 22. So 3.2 exponent 22 divided by 3 times 1.3 exponent negative 7. Okay, so that is 8.2 times 10 power 28. 8.2 times 10 power 28. Then for wire X, calculate the average drift speed of the free electrons. So average drift speed, we say the current is never. So the average drift speed is going to be the current divided by NE times A, which is going to be current is 0.80. N is going to be 8.2 times 10 power 28. The area was given as 1.3 times 10 power negative 7. And then the charge of each electron is 1.6 times 10 power negative 19. So I'll just simply say 0.8 divided by, open brackets. I'll open two brackets, 8.2 exponent 28 times 1.3 exponent negative 7 times 1.6 exponent negative 19. And we close that bracket, which gives us 4.7 times 10 power, 4.7 times 10 power negative 1, 2, 3, 4, power negative 4. 4.7 times 10 power negative 4 meters per second. A wire Y has the same cross-sectional area as wire X and is made of the same metal. Wire Y is longer than wire X. Wire X in the circuit is now replaced by wire Y. So it has the same cross-sectional area and same metal. That means same resistivity. Note that resistance is equal to rho L over area. So area is the same, resistivity is the same, but it is longer. So resistance is higher, so the current is smaller. Assume that wire Y has the same temperature as wire X. State and explain whether the average drift speed of the free electrons in wire Y is greater than, the same as, or less than that in wire X. So we have seen, because resistance is directly proportional to length, wire Y has a larger resistance. Wire Y has a larger resistance. Wire Y has a larger resistance. We have seen resistance is equal to rho L. Resistance is equal to rho L over area. So rho is the same metal. Area is the same, but is longer. So wire Y has a larger resistance and therefore has a smaller current. So has a smaller current. It has a smaller current. And if the current, we can say the resistance increases, the current decreases. And from V is equal to I over NEA. If the current is smaller, it means the drift speed is decreases. So the average drift speed is less. So the average drift speed is less in wire Y. The average drift speed is less in wire Y than in wire X. Okay. A resistance wire of uniform cross-sectional area 3.3 exponent -7, length 2 meters, is made of a metal resistivity 5.0 exponent -7. Show that the resistance of the wire is 3 ohms. So we know that resistance is equal to rho L over cross-sectional area. So everything was given, we just substitute. Rho is 5.0 times 10 power -7. L is 2.0. Area is 3.3 times 10 power -7. 5 exponent -7 times 2 divided by 3.3 exponent -7. So that is 3.03, which is approximately 3.03 recurring, which is approximately 3.0 ohms. The ends of the resistance wire in A are connected to the terminals X and Y in the circuit shown in the figure. The cell has an EMF of 1.5 volts and internal resistance R. The potential difference between X and Y is 1.2 volts. Calculate the current in the circuit. So current is equal to V divided by R, which is equal to, the V is 1.2, since they gave us the PD across XY is 1.2, and the resistance is 3. So they are in series, so I'll just divide by 3.0. The resistance is 3. They are in series. The Y is in series with the battery. So that is 1.2 divided by 3, which is 0.4. 0.40 amperes. Then the internal resistance. So we know that EMF is equal to the terminal PD plus the lost volts. So the EMF is 1.5 is equal to the terminal PD. The PD outside is 1.2 plus the lost volts. The lost volts is going to be current times the internal resistance. Therefore, the current, remember, is 0.4. So 1.5 minus 1.2 is equal to the current, which is 0.4 times the internal resistance, which when I check with the calculator, 1.5 minus 1.2 divided by 0.4, that is 0.75. So R is 0.75. A galvanometer and a cell of EMF E with negligible internal resistance are connected to the circuit in B as shown in the figure. So that's what we have. The resistance wire between X and Y has length 2 meters. So the length of the wire is 2 meters. The galvanometer has a reading of 0 when the connection P is adjusted so that XP is 1.4 meters. So XP is 1.4 meters. Note that the resistance of the wire was 3 ohms. So I can first of all quote the resistance per unit length. The resistance per unit length, resistance here was 3 ohms. And the length of the wire is 2 meters. Resistance per unit length will be 3 over 2 ohm per meter. Determine the EMF E of the cell. Determine the EMF E of the cell. So the EMF E of the cell is going to be equal to the PD across XP. And the PD across XP is going to be equal to the current through XP is going to be the current through XP times the resistance of XP, because the resistance C per meter length, what is the resistance per meter length? Okay, let me just use a simple scenario where we have a PD across, the PD across each of these. So the PD across XP is going to be actually the EMF. But note that the length XP, the ratio of the length XP to the total length is going to also be directly proportional to the PD across each of these wires, which is actually going to be directly proportional to actually the resistances of these wires. Therefore, I'll simply say that PD across XP over the PD across XY is going to be equal to the length of XP over the length of XY. The PD across XP is still going to be EMF, and the PD across the wire XY is going to be, the PD across the wire XY was, I think it was given as 1.2. This was 1.2 volts from part A, from the previous part B actually. So I'll simply divide this by 1.2, should be equal to the PD across, the length XP, which length XP is 1.4 over the length XY, which is actually 2. In other words, it is equivalent to either using resistance per meter or the PD per meter, which would be, of course, the PD per meter here would be 1.2 divided by 2. That would be volts per meter. That is the PD per meter. So to find the PD corresponding to 1.4 volts, I just multiply the PD per meter times 1.4. So that means the EMF E is going to be 1.4 over 2 times 1.2. So that will be 1.4 divided by 2 times 1.2, which is 0.84. The circuit in the figure is modified by replacing the original resistance with the second resistance wire. The second wire has the same length as the original wire and is made of the same material. The second wire has a smaller cross-sectional area than the original wire. That means it could be having a greater resistance. Connection P is adjusted on the second wire so that the galvanometer again has a 0 reading. State and explain whether length XP for the second wire is shorter than, longer than, or the same as. So we have seen the ratio of the lengths with the PDs. Length XP over length XY should be equal to PDXP over PDXY. So the length XY is not going to change, it is the same. But they are saying the circuit in the figure is modified by replacing the original resistance wire with the second resistance wire. The second resistance wire has the same length, so XY is the same, and it's made of the same material. Resistivity is the same. And resistance is equal to rho L over cross-sectional area. So the second wire has a smaller cross-sectional area. So L is the same, rho is the same, smaller cross-sectional area means a greater resistance. So it means the PD across the second wire is going to be greater, which means PDXY is now bigger. PDXY is now bigger, yet length XY is not changing. So if we want the reading of the voltmeter again to be 0, what should happen to LXP? So since the second wire has now a greater resistance, the PD across it is greater, and therefore the length XP is going to be shorter because they are actually inversely proportional. You can see from that expression. So the second wire has a larger resistance. The second wire has a larger resistance. So the PD across XY is greater because PD is equal to IR. The PD across XY is now greater, or is now larger, or you can say increases, is now larger for the second wire. The PD across XY is now larger for the second wire. So the length XP for the second wire is shorter because they are inversely proportional. So the length XP for the second wire is shorter. We see from this expression that they are inversely proportional. Okay. The ends of a metal resistance wire are connected to a battery of EMF 80 volts and negligible internal resistance as shown in the figure. The power dissipated by the resistance wire is 36 watts. Calculate the current in the resistance wire. So we know power is equal to I times V. So the current is going to be power, which is 36, divided by V, which is 8.0. So 36 divided by 8, which is 4.5. So that is 36 by 8.0, that is 4.5. Then the number of free electrons that pass through the resistance in a time of 50 seconds. So we know that charge is equal to current times time. But charge is equal to the number of charge carriers times the charge of 1. Number of electrons is going to be I times T over E, which is going to be, I think they gave us the charge. So this is going to be 4.5 times time, which is 50, divided by 1.6 times 10 power negative 19. 4.5 times 50 divided by 1.6 exponent negative 19. So that is 1.4 times 10 power 21. 1.4 times 10 power 21. The resistance of the wire is now what we want to find. We have been given that the power and the PD. So from power is equal to V squared over R, it means the resistance is going to be V squared over the power, which is going to be 8 squared divided by 36. 8 squared divided by 36, which is 1.77 recurring, 1.78 or 1.8. The metal of the resistance wire in the circuit has resistivity 1.4. The cross-sectional area of the wire is 0.25. We change this by multiplying it by 10 power negative 6 to change it to meters squared. Determine the length of the wire. So earlier on we have already seen that resistance is equal to rho L over cross-sectional area, meaning that the length is going to be R times A divided by rho, which will be we have seen R is 1.8 in the previous part. Cross-sectional area is 0.25 times 10 power negative 6 to change it to meters squared, divided by the resistivity, which is 1.4 times 10 power negative 6 ohm meters. 1.8 times 0.25 exponent negative 6 divided by 1.4 exponent negative 6. So that is 0.32. So the length is 0.32 in meters. The circuit shown in the figure 6.1 is modified by replacing the original resistance wire with the second resistance wire. The second wire has larger diameter than the original wire. Remember, resistance is equal to rho L over area, and area is equal to pi d squared over 4. So resistance is equal to rho L times 4 over pi d squared. Okay. So there are no other differences between the second wire and the original wire. That means rho is the same, L is the same. By reference to resistance, state and explain whether the power dissipated by the second wire is more than, less than, or the same as the power dissipated by the original wire. So we see that the resistance is greater. So because the diameter has been increased, the second wire has a larger cross-sectional area. It has a larger cross-sectional area. It has the same length. It has the same resistivity. It has the same resistivity. And therefore, since resistivity is the same, length is the same, so it has less resistance. And so, less resistance. It has a smaller resistance. And if it has a smaller resistance, for the same PD and more current, it means that there will be more power dissipated. For the same PD and more current flowing, since the resistance is less, then it means there will be more current dissipated. So if for the same PD, more current is flowing, so more power dissipated. For the same PD across the wires, for the same PD, more current flows, through the wire, so more power dissipated. So if you use power is equal to IV, for the same PD, there's more current flowing since the resistance has decreased, so there's more power dissipated. Or if power is equal to V squared over R, the resistance is now smaller. For the same PD, the power dissipated is going to be greater. The circuit shown in figure 6.1 is modified by connecting a second battery of EMF 8.0 volts and negligible internal resistance in parallel with the original battery and the original resistance wire as shown in the figure above. By reference to the current in the resistance wire, state and explain whether the addition of the second battery causes the power in the original resistance wire to decrease, increase, or stay the same. Of course, the current through the batteries is smaller because it divides at the junctions, but total current through the wire has remained the same. The total PD across the wire is still going to be 8 volts. So it means the current in the wire is going to remain the same, and therefore the same PD across the wire, so the power stays the same. Although the current in the batteries themselves is smaller, because the effective EMF, the effective PD across the battery will not be 8 volts when they are connected in parallel. In fact, the effective will be less, that will be half of 8. But the total current coming out here will still be the same. So we are saying the current in the wire is the same. Is the same. The current would only change if they were connected in series. The current in the wire is the same, and the PD across the wire is the same. PD across is the same. So the power stays the same. So the power stays the same. State Kirchhoff's first law. I think we are stating this law for almost the last time in this document. So Kirchhoff's first law, the algebraic sum of all currents at a junction is zero. Algebraic sum of currents. Algebraic sum of currents at a junction is zero. Algebraic sum of currents at a junction is zero, or the sum of currents into a junction is equal to the sum of currents out of a junction. A battery is connected to two resistors, X and Y, as shown in the figure. You see that they are in parallel. The resistance of X is greater than the resistance of Y. If X is greater than Y, it means the current in X is smaller than the current in Y. State and explain which resistor dissipates more power. So the PD across them is the same because they're in parallel. And the power is equal to V squared over R. V is the same because they're in parallel, but X has a greater resistance. If it has a greater resistance, it means the power dissipated is smaller. So you can say same potential difference, same PD. There is same PD across X and Y as they are in parallel, or because they are in parallel. That's number one. But power is equal to V squared over R. Power equals to V squared divided by R. And since Rx is greater, and since resistance of X is greater than resistance of Y, then the power of X is going to be less. So it is greater in Y. So Y dissipates more power. Then Y dissipates more power. Because power is inversely proportional to the resistance, the one with the smaller resistance dissipates more power since the PD is the same. The two resistors are made of wires that have the same length. Both wires are from the made of the same resistivity. State and explain which resistor is made of wire with the larger cross-sectional area. So resistance is equal to rho L over cross-sectional area. And remember, rho is the same, L is the same. And resistance of X is greater than resistance of Y. So remember, resistance is inversely proportional to cross-sectional area. The one with the greater resistance must be having a smaller cross-sectional area. So the question is state and explain which resistor is made of wire with a larger cross-sectional area. So that should be Y. So it says so Y has the larger cross-sectional area. So Y will have the larger cross-sectional area. Okay. A battery of EMF 9 volts and negligible internal resistance is connected in series with an LDR and a fixed resistor of resistance 1800 ohms as shown in the figure down there. A voltmeter is connected across the fixed resistor. The reading on the voltmeter is 5.4 volts. So the PD here is 5.4 volts. Calculate the current in the circuit. So current is going to be equal to V over R. Since we have the PD across 1800 ohms, I'll just use 5.4 over 1800. So that is 5.4 divided by 1800, which gives us 3.0 times 10 power negative 3. Then calculate the resistance RL of the LDR. So we have the total current in the circuit, and the easiest way is to look at the current as being equal to the EMF over total resistance. So the current is 3 times 10 power negative 3, which will be equal to the EMF. The EMF is given as 9 volts over total resistance, which will be 1800 plus resistance of the LDR, that is RL. So it means RL plus 1800 is equal to 9 divided by 3 times 10 power negative 3. So I'll just press my calculator. 9 divided by the answer minus 1800. So that's 1200. The intensity of the light illuminating the LDR increases. By reference to the current in the circuit, state and explain the change, if any, to the voltmeter reading. So if the intensity of light in the LDR increases, intensity here increases, it means our resistance of L decreases. If the resistance of L decreases, it means the PD across RL becomes smaller, which means the PD across 1800 must become greater by conservation of energy. So that is very easy. So the resistance of LDR decreases. So current in the circuit, of course, if the resistance of the LDR decreases, total current in the circuit increases. Current in the circuit increases. So if current in the circuit increases, so it means the PD across 1800 ohms increases. So the voltmeter reading increases. So the voltmeter reading increases. In other words, the PD across RL decreases, so the PD across 1800 must increase. A network of 3 resistors of resistance R1 and R2 and R3 is shown here. The individual PD is shown V1, V2, and V3. The current is I. The combination has PdV, so total PdV is equal to V1 plus V2 plus V3. But remember, by Ohm's law, V is equal to I times R. Therefore, I times R is going to be equal to I times R1 plus I times R2 plus I times R3. The current is the same. So there is a common factor of I, so IR is equal to I into R1 plus R2 plus R3. So I cancels out, so R is equal to R1 plus R2 plus R3 because I cancels out. A battery of EMF 8.0 volts and negligible internal resistance is connected to a thermistor, a switch X, and 2 fixed resistors as shown here. Resistor R has a resistance 6 kilo ohms. R2 has 4 kilo ohms. R1 has 6 kilo ohms. R2 has 4 kilo ohms. Switch X is open. So this one is out of play. These two are in a series. Calculate the potential difference across R1. So these are potential dividers. So PD across R1 is going to be resistance R1 over total resistance, which is R1 plus R2 times the voltage supply. So that is going to be R1 is 6 kilo ohms over 6 plus 4 kilo ohms, then times the voltage supply, which is 8. So 6 divided by 10 times 8. That is 4.8 volts. Switch S is now closed. The resistance of the thermistor is 12 kilo ohms. Calculate the current in the battery. So if switch X is now closed, we now have resistors in parallel, and this is now this is 12 kilo ohms. So let's first find the total resistance in parallel. So resistance in parallel is going to be the product over the sum. There are only two. So I'll say product 4 times 12 over the sum 4 plus 12, which is that is 4. I think that is 48 over 16. 48 divided by 16, which is 3. 48 over 16, that is 3 kilo ohms. So that is total resistance in parallel. So now we can find total resistance. R total is now 3 plus the other resistor in series, which is 6. So it is 3 plus 6. It is 3 plus 6, which gives us 9 kilo ohms. So now we are finding the current. Total current is equal to the EMF divided by total resistance, which will be EMF was 8. Total resistance is 9 times 10 power 3. So 8 divided by 9 exponent 3, which is 0.08888 recurring. So 0.000889, or I'll just say 8.9 times 10 power negative 4. That is 1, 2, 3, 4, power negative 4. The switch X is in the circuit in B remains closed. The temperature of the thermistor decreases. That means the resistance of X increases. The resistance of the thermistor increases. So total resistance of the circuit is going to be increasing because the resistance of the thermistor increases, total resistance increases. The current through the battery decreases, which means the PD across the parallel combination is higher, but the PD across R1 becomes lower. By reference to the current in the battery, state and explain the effect, if any, of the decrease in temperature on the power produced by the battery. Okay, the power produced by the battery, remember, is E times I. Reduction in temperature means increase in resistance. Total resistance increases, the current flowing through the circuit becomes smaller. So the power produced by the battery decreases, becomes smaller. So we can say thermistor resistance increases. Thermistor, I think thermistor ends with the O. Thermistor resistance decreases, increases with the temperature. Thermistor resistance increases with temperature. Remember, it is inversely proportional. We call it negative temperature coefficient. Increases. So, total resistance increases. And if total resistance increases, the current in the battery decreases. The current in the battery decreases. Then from power is equal to E times I, and E is constant, so power decreases. Okay, so the power decreases. On the figure, sketch the IV characteristic of a filament lamp. We have been seeing this many times. So a filament lamp initially, as V increases, it also conducts, so I will increase the weight, the thickness slightly. So initially, as V increases, the filament lamp also conducts, but then as V increases, the temperature of the filament increases so that the current flowing becomes, the current reduces. So this line will curve that side, it will also curve this side, something like that. As V increases, the current flowing becomes almost constant. That means the resistance at high temperature, the resistance increases. So the current, I don't want to make it horizontal. The line cannot be made horizontal because it means when you make it horizontal, it means you have reached infinite resistance, which may not be practically possible to arrive at. So that's why the gradient is decreasing, but has not yet become horizontal, as you see from the graph. So it is supposed to be a line in the first and the third quadrant only and only, and the gradient becomes less steeper on both sides. The gradient becomes less steeper. Okay, explain the shape of this line. So that is very simple. To explain the shape of this line is extremely simple. As current flowing increases, the temperature of the filament is also increasing. So as I increases, the temperature of the filament increases. As the current increases, the temperature of the filament increases, and as the temperature increases, the resistance of the filament also increases. Remember, temperature is directly proportional, resistance is directly proportional to temperature. So as temperature increases, and as temperature increases, the resistance of the filament increases. The resistance of the filament increases. So the graph curves because the ratio I over V decreases. So then the graph will curve. The graph curves because the ratio I divided by V decreases. Of course, if I over V decreases, it means V over I increases. So you could say, oh, V over I increases. So that's why the graph curves. As I increases, the temperature of the filament increases. And then as temperature increases, the resistance of the filament increases. So if the resistance increases, then it means the graph curves. That means the ratio I over V is decreasing. the ratio I over V decreases. A conducting wire has length 5.8 and cross-sectional area 3.4 exponent -8. The resistivity is 5.6 exponent -8. Calculate the resistance of the wire. So we now know that resistance is rho L over cross-sectional area. Rho is 5.6 times 10 power -8 times the length 5.8 divided by cross-sectional area, which is 3.4 times 10 power -8. So we have 5.6 exponent -8 times 5.8 divided by 3.4 exponent -8. So that gives us 9.6 ohms. I think this is the last part of the question. Yes. A resistor of resistance R is placed in a circuit with a cell of negligible internal resistance, two switches S1 and S2, a second resistor of resistance 2R, and three ammeters X, Y, and Z. The circuit is shown in the figure. Okay. So the reading on X is 1.0 when S1 is open and S2 is closed. So when this is closed, the reading here is 1.0. And note that if this is closed, if S2 is closed, this is going to be in series. So the reading here should also be 1.0 because they're in series. The reading of Y should be 0 because the circuit is open. So they are telling us to complete the table. S1 open, S2 open, dot 1 has been completed. S1 is open and S2 closed. X is 1.0. That means Y is also going to be 1.0 because they are going to be in series. They are going to be in series. When S2 is closed, X is 1.0, meaning Z is also going to be 1.0. And then Y is going to be 0, not 1.0. Y is going to be 0 and Z is 1.0. This is going to be 1.0. Sorry, Y is 0 and Z is 1.0. Then they are now closing, S1 is being closed and they are opening S2. So S2 is open. If S2 is open and S1 is closed, so R is in series. Note that the resistance of R is half of that of 2R. If the current was 1.0 when the resistance was 2R, now that the resistance is R, the current is supposed to double. So the current will be twice 1.0. So the current here is going to be, the current in Y is going to be 2.0, even here to be 2.0 because they will be in series. I'm repeating this. If when we had a resistance of 2R, the current was 1.0, that means now when the resistance is halved, the current must double. Because these two are in parallel, the PD is the same. So when the resistance is doubled, when the resistance is halved, the current must double. That's why I'm showing this as 2.0, 2.0. So Y is 2.0, X is 2.0, Z is open because S2 is open, Z is going to be 0. So that is 0. Now both are closed. Both are closed. So if both are closed, remember the current here was 2.0 and the current here was 1.0. So 1.0 and 2.0, it means the total current now is going to be 3.0. So we just sum up. So for X will read the total current, which is 1.0 plus 2.0, that is 3.0. Y, of course, Y will also read 2.0 because the current here is remaining 2.0, and then Z will read 1.0. So this is 1.0. So that marks the end of that. That marks the end of electricity. I am very certain that at least you have learned something from all these questions. There could be errors, but just remember the teacher is human, is bound to make mistakes. In case of anything which is not clear, or in case of anything that you think is a mistake, you can just send me, just write a comment. I will read through the comment and rectify where possible. Nevertheless, that is the end of AS Physics Paper 2. The next will be AS Physics Paper 1, that is solved multiple choice questions. All the best. Have a blessed time. Bye bye.